Olá, muito boa tarde. Iniciamos agora a nossa reunião anual do Gege. O Grupo de Estudos em Geodésia Espacial inicia com as nossas apresentações um breve conglomerado de como foi todas as apresentações desde 97 até 2025. Gostaria de chamar para uma palavra inicial o professor João Francisco Galera Monico. Professor Galera, fique à vontade.
Olá, pessoal. Boa tarde a todos. É uma satisfação muito grande estarmos aqui realizando mais uma vez o Gege Anual, 2025, neste caso. A programação realmente está muito interessante e eu espero que todos aproveitem. Quero agradecer aqui aos palestrantes por ter aceito esse convite, alguns deles do outro lado do mundo, na hora de dormir, está aí esperando o horário para fazer a apresentação. Então, nós teremos aqui uma apresentação inicial da histórico do Gege, que será feita pela Daniele. Depois nós vamos ter umas palavras da China, Dr. Caigu, vai falar sobre CNS ATM, da Universidade de Beirã, onde eu tive a oportunidade de visitar há pouco tempo. Nós teremos aqui novamente o nosso colega Dimitrios Pitska, da European Space Agency, que vai falar sobre PPP-AR, outro assunto de bastante interesse. E convidamos também o Benedict Soja, do Space Geodesy de Zurique, que irá falar sobre um assunto que hoje é muito importante, não só na área de geodésia, mas em todas as ciências, que é a inteligência artificial. Então, ele vai falar sobre Shaping the Future of Geodetic Earth Monitoring with AI. E, finalmente, nós teremos a presença do Roberto Luz, Dr. Roberto Luz, da Coordenadoria de Geodésia, Coordenação de Geodésia do IBGE, que falará sobre a rede vertical brasileira. Então, muito obrigado a todos os palestrantes e também muito obrigado aos que estão aí nos acompanhando, quer seja presencialmente aí na Unesp, em Presidente Prudente, ou virtualmente via YouTube. Cada apresentação, ao final, nós temos aí, no geral, 45 minutos reservados para isto. Então, o palestrante vai fazer a sua palestra em algo em torno de 35, 40 minutos, e nós teremos algum tempo para questão, que poderão as perguntas serem enviadas via o YouTube, ou se isso não estiver correto, o João Zalpa me corrige aí um pouco isso, tá bom? Então, um bom evento a todos e aproveitem.
Bom, pessoal, seguindo com o que o professor Galera falou, exatamente, aqueles que estarem na presença virtual, por favor, aqueles que precisarem mandar alguma sugestão, comentário, dúvida, pode ficar à vontade para utilizar o chat do YouTube. Aqueles que estão aqui presencial, por favor, apenas levantem a mão para fazer as mesmas perguntas, ou questionamentos, ou também sugestões. Vamos para a primeira apresentação da nossa reunião com a professora Daniele Barrocá. Professora Daniele, fique à vontade.
Boa tarde a todos. Meu nome é Daniele Barrocá, sou professora aqui do Departamento de Cartografia da Unesp e coordeno o GG juntamente com o professor Galera. Então, hoje eu vou fazer para vocês uma apresentação rápida de um pouquinho do nosso histórico. O GG foi iniciado em Presidente Prudente em 96, inspirada no grupo GBS da Universidade Técnica de Delft, na Holanda, liderado pelo professor Peter Dempsey. Aí nós temos o Galera, professor Peter. Ele iniciou, quando o Gege iniciou na Unesp, com um pequeno grupo, apenas um docente e 2 alunos. Em 96 foi aprovado um projeto de jovem pesquisador que auxiliou então, o crescimento do Gege. Outros docentes começaram a participar e, principalmente, com a criação do programa de pós-graduação em Ciências Cartográficas, o Gege vem se fortalecendo. Eu iniciei no Gege em 2002, na verdade, 15 de 2001, eu era aluna, iniciando o mestrado com a orientação do professor Galera, e hoje, então, sou professor do departamento e coordeno juntamente com o nós fazem parte do Gege docentes, pesquisadores, alunos, bolsistas de iniciação científica, mestrandos, doutorandos, pós-doutorandos, estagiários da área de geodésia, topografia, e essas reuniões ocorrem quinzenalmente, e nós discutimos assuntos relacionados à geodésia.
O microfone posicionou mais na boca? Pode tirar. Ok.
Nós também temos um termo de referência do Gege, com algumas regras, algumas obrigações, deveres. Em geral, se organiza um seminário anual com duração de um dia. Nós geralmente fazemos no final do ano. E já foram realizados em torno de 12, além de workshops de projetos, que também fazem parte das atividades do Gege. Além disso, o Gege está inserido como uma disciplina do programa de pós-graduação em ciências cartográficas, onde eu e o professor Valéria somos os docentes, e ela oferece créditos tanto para mestrado como para doutorado. Essa é a página do grupo no CNPq, então é um grupo do CNPq. Quem tiver interesse pode entrar aí no link, né, do CNPq. Quais são os nossos objetivos? Investigações sobre o uso do sistema GNSS para fins de geodésia, monitoramento da atmosfera, integração com outras ciências e engenharias. Que seria o nosso posicionamento e sensoramento remoto de geodésia. Também trabalhamos com implementação e validação de novas metodologias para posicionamento espacial e aplicações não convencionais. Temos uma gama muito grande de aplicações, enfim, de pesquisas que realizamos. Aqui nós temos o número de reuniões anuais, fizemos aí um gráfico. Fizemos aí um gráfico desde 2002 até 2025. Vocês podem ver aí, chega em torno de 20, esse ano 21, 22 reuniões, mas a gente se mantém aí em torno de 15 a 20 reuniões por ano. O número de membros, ele vem crescendo, depois eu vou falar um pouquinho disso, mas principalmente porque antes éramos um grupo presencial, apenas aqui na FCT, e depois, com a pandemia, quando começamos a abrir esse grupo para outras universidades, outros membros externos, isso tudo nos proporcionou um número aí muito maior de membros no país. Qual é a nossa realidade atual? Em 2019, passou a ser um nível nacional, como eu disse, com participação de grupos da UFPE, da Federal do Rio Grande do Sul, UFPR, UFO, além da Unesp. Atualmente, outras instituições também vêm participando assiduamente, como pesquisadores do INPE, o FPI, o Unicamp, e há um controle de frequência, a gente sempre faz isso pelo chat, enfim, para verificar, né, como que estão as nossas reuniões. Para vocês terem uma ideia, né, nós fizemos assim, não a partir de 2002, que ficaria coisa demais, em 98, nós fizemos aí só nos últimos 4 anos. Por exemplo, em 2020, nós tivemos 16 reuniões mensais, 16 reuniões durante o ano. Essas reuniões sempre ocorrem às sextas-feiras, às 16 horas. E hoje a Gege não parou, né? Mesmo durante a pandemia, nós continuamos com todas as reuniões. Nesse ano foi organizado o Seminário Anual do Gege, com apresentações de pesquisadores internacionais, líderes, né, na área, pesquisa sempre representando aí o estado da arte da geodésia, que tem de mais atual na nossa área. Geralmente nós transmitimos, então, por YouTube, aí nós temos aí a média de participantes. Nesse ano, nós tivemos aí algumas participações, não vou entrar em detalhes devido ao tempo, mas está lá no YouTube, quem tiver interesse de assistir, pode entrar e assistir, fica lá armazenado. Em 21, 15 reuniões. Também tivemos o Seminário Anual do Gege, com apresentações relacionadas ao INCT, GNSS Navier, sempre em dezembro. Tivemos aí outras importantes participações nessa reunião. Em 22, 17 reuniões, além de colegas de outras instituições, enfim, sempre temos. Também foi organizado o Seminário Anual, e vocês podem ver também outros palestrantes de renome na área de geodésia. Também tivemos a celebração de 25 anos do Gege em 2022. Ainda tinha até gente ginástica, a gente já estava saindo da pandemia, tivemos aí essa reunião presencial. Em 23 foram 17 reuniões. Não foi organizado o Seminário Anual do Gege, mas ocorreu um workshop do ICT Geodésia Espacial. Então, por conta disso, nós não realizamos o Gege.
Opa.
Gravou?
Aí.
Em 25, vamos falar desse ano, então. Nós tivemos 17 reuniões durante o ano. Nós tivemos 2 transmissões no YouTube, a ameaça do bloqueio do sinal de GPS no Brasil, que foi aí umas informações que não estavam muito corretas, então nós fizemos uma reunião para falar um pouquinho sobre isso. E também tivemos um Gege especial em comemoração à aposentadoria do professor Milton Shimabukuro, que também transmitimos, está tudo ali no YouTube, para quem tiver interesse. Então, hoje temos o nosso Gege anual. Nós temos aí tudo no YouTube, para quem tiver interesse, com muitas visualizações. Aqui, além disso, nós temos as mídias sociais, nós temos o Instagram, enfim, todas as mídias sociais aí estamos sempre divulgando as atividades do grupo. Então, se vocês quiserem nos seguir, vocês sempre vão ficar aí atualizados na área de geodésia. Nós fizemos no decorrer desses anos, alguns quadros. Nós fizemos destaques do Gege, nós fizemos mulheres na geodésia, enfim, alguns quadros do Gege também nesse período. Para vocês terem uma ideia, nesse período de 22 a 25, que nós temos trabalhado mais com as mídias sociais, nós tivemos 294 conteúdos postados, 645 mil visualizações, 55 mil curtidas, 1.364 comentários, 8.800 compartilhamentos, além de 5.325 pessoas que salvaram o nosso conteúdo. Então, a gente tem aí ajudado bastante a comunidade de geodésia. A gente sempre gosta de, no final, falar um pouquinho, refletir um pouquinho sobre o Gege. A gente sempre pede que os orientadores, os participantes dos grupos, os professores, eles incentivem a participação efetiva nas reuniões, trazendo reflexões, perguntas sobre a área. É claro que, talvez, mesmo sendo apenas geodésia, nós temos várias áreas dentro da geodésia. Às vezes não é sua área de pesquisa, mas é algo que você pode aprender, que você pode ampliar o seu conhecimento, então é muito importante que, inclusive, os alunos de graduação participem dessas reuniões. Além de prestigiar as apresentações dos colegas e ampliar a divulgação das pesquisas nas mídias em uma linguagem didática para o público em geral. Isso a gente busca com as mídias sociais, trazer a geodésia mais próxima do dia a dia das pessoas, para que elas entendam, né, onde está essa geodésia no dia a dia de cada um. Bom, é isso, uma apresentação rápida, só para fazer um histórico. Obrigada a todos.
Bom, pessoal, indo para a nossa próxima apresentação do dia, gostaria de chamar aqui o professor Gege, da Universidade de Beirã, para fazer a segunda apresentação do nosso Seminário Anual do Gege. So, moving on the next presentation, we would like to invite Professor Gege from Beirã University to do his presentation. Gege, make yourself at home and may you have a good presentation.
So, hello everyone. I hope you can hear me clearly.
Yes, it's clear.
Nice to see you guys. Let me try to share my screen now. So, can you see my screen?
Yes.
Okay.
Can you do the presentation form of the PowerPoint? We are just only seeing the PowerPoint screen, but not the presentation form.
Yeah. So to save some internet, I will turn off my camera. And let's move on. Okay. So many thanks for the invitation for this presentation. I'm Kai Guo from China. Actually, it's the School of Electrical Information Engineering and the State K Laboratory of CS and ATM from Beihang University. Yeah. And my topic today is the CS ATM group at Beihang University. And I also want to present some of my recent progress on the air navigation performance evaluation using ADS-B. So let's move on. So first about me. Currently, I'm an associate professor at Beihang University, and I'm also the technical advisor of the International Civil Aviation Organization Communication, Navigation, and Surveillance Panel nominated by China. I got my PhD from the University of Nottingham in August of 2021. I'm also a Merit Carry Action ITN Fellowship by the European Union in 2017. During my PhD study, I had some academic visits to Polytech de Torino, São Paulo State University, the UNESCO, and also the Hong Kong Polytechnic University. So let's move on. So in this presentation, first I want to introduce my lab and also my group. Then I also want to propose some potential collaborations. Sorry, this should be collaboration. It's a typo here. Then the airborne GNSS performance evaluation with ADS-B in the last section. So currently I'm in the State K Laboratory of CS and ATM, and this lab is a national lab focused on advancing technologies in air traffic management and air navigation systems. The major interests including the communication, navigation, and surveillance, which is the CNS, and also the new techniques of the advanced CS and ATM, and also the software and hardware development in the lab. The organizations of the lab is mostly by Beihang University, which is called BUAA, the Beijing University of Aeronautica and Astronautica, which is the former name of my university, and also the in cooperation with the Beijing Institute of Technology, the BIT, and Aviation Data Communication Corporation, which is ADCC. So this is a lab managed by different entities. And in my lab, we have different type of topics. For example, the integrated aviation communication by satellite and ground infrastructures, and then it's aeronautical multi-source resilience navigation, which is more related to our meeting today. And third one, we have the integrated 4D management and control and intelligent airspace traffic management, and also the CS performance test and verification. And we have different groups in our lab. For example, the aviation communication group, aviation navigation and testing group, aviation surveillance group, the avionics group, and the collaborative management group, and the flight inspection group. So we have more than 80 professors and more than 100 doctor students and more than 200 master students. So it's quite a large lab. And I am based in the aviation navigation and testing group in our lab. And we have, in our group, we mostly focus on the aviation functionalities. And we also have some different research topics. For example, the satellite-based navigation, we works on the navigation argumentation, like the ground-based, satellite-based, and airborne-based argumentation, the G-bus, S-bus, A-bus, and the LEO-based argumentation. And also the prototype development, like the MMR, the multimodal receiver. The multimodal receiver will mentioned several times in my presentation. I will show you more details later. And also the interference detection and the mitigation, like the ionosphere and the jamming and spoofing interference, and also some experiment and test. So we have different platforms like the UAV and the private jet for the test. And we also have the multi-sensor fusion navigation topics like the vision-aided aircraft landing to solve the problems if there is no GNSS signal when the aircraft is landing. And also the navigation in harsh environment, like in the cities or in remote regions where the GNSS signal may be blocked or interferenced. We have some platform to do the integrated navigation. Yeah. And also the integrated navigation and communication topics. One of the topic is the L-band digital aviation communication system to be used for ranging and navigation. And also the alternative PNT during the GNSS outages, like the DME, VOR, and LDAX based navigation. The DME is the distance measurement equipment, and the VOR is the very high frequency omnidirectional range. DME and VOR are all navigation means for aviation, actually. And let's move on. So some highlighted work, like we have the G-bus, airborne and ground integrated monitoring software developed, and we have the BDS precision approach and the landing guidance system. And with the support of our lab, we have installed and construct different ground stations at Shandong Dongying Airport, Shanghai Airport, Zhoushan Airport, and Tianjin Airport. In terms of the S-bus, one of the topic is the DFMC, is the dual frequency multi-constellation S-bus software receiver, and also the S-bus performance evaluation platform. And some tests are conducted currently in our lab for the BDS S-bus. And also the ionosphere monitoring. We developed the ionosphere anomaly monitor and prediction platform based on the intermediate frequency measurement, which can provide more detailed information for ionosphere anomalies like scintillation. And the two stations are installed in China, one in Sanya Airport, which is the very source of China. Another one in Guangzhou province, Guangzhou city, in one of the universities in Guangzhou. Another topic is the impact assessment of ionosphere anomalies based on ADS-B data, which will be the focus of my presentation today. So I will show the detailed results later. And then it's multimodal receiver. The multimodal receiver is the receiver dedicated for aircraft use. It is installed on the aircraft or airplane to do the navigation and positioning. So the multimode means that there are different modes of navigation. For example, the VOR and ILS. ILS is the instrumental landing system used for the landing of the aircraft, and the VOR is the angle measurement for the aircraft. So another important part in the MMR is the GNSS receiver. For example, the GPS receiver, the Galileo receiver, or the BDS receiver. So different type of receivers are integrated in one equipment like this. So this is the multimode receiver, and this is widely used in commercial aircraft, actually. And we also did some tests with our in our lab, like the communication, navigation, surveillance equipment functionality and performance test. For example, the electromagnetic interference test and simulation platform. Also, we have the astronautical navigation and surveillance vertical platform. And some other work related to the test of the navigation functionality, both on the ground and in the air. We did some tests from Beijing to the far east of China, and we did some tests with UAVs and commercial aircraft, for example here, and commercial aircraft from from Boeing to investigate the G-bus performance in China with the support of our lab, actually. And we collected lots of data and to do the analysis. So that's the equipment and the software. Then we also supporting the International Civil Aviation Organization for the standardization of the BDS. So currently BDS is one of the one of the system that is included in the International Civil Aviation Organization standards. This is the support from our lab to do the validation of the BDS techniques. And some potential collaborations from my side. So we are open for all different type of collaborations, like the co-authored publications, like multinational projects, like for example, the cooperation agreement in the framework of National Natural Science Foundation of China, the NSFC, the National K Research and Development Program of China, and also BRICS SDI Framework Program, and also the European Open Funding opportunities. Another type of collaboration might be the students exchange and visiting scholars short-term segments. We have various funding opportunities from China Scholarship Council for international students with a very excellent, with a very high supporting high level, supporting lots of money actually. Yeah, and we can also do some co-chair sections workshops in the international conference organizations like the European Navigation Conference and Digital Avionics System Conference and so on. Yeah. Here are some examples in our lab. We have students from different countries, for example, from Italy, from France, and from Canada. And every year we host some, we have some class for international students on the BDS Beidou navigation system. And we have internship students from France almost every summer holiday. Yeah. So here are just some examples. And finally, let's move to the topic on the airborne GNSS performance evaluation with ADS-B. So first is a problem statement. So the airborne GNSS performance evaluation during the geomagnetic storm. So this is a very popular topic because we found that the airborne GNSS performance during geomagnetic storm were widely investigated, but with the ground-based data, which means that it is like a simulation. So people want to study the airborne GNSS performance, but they use the ground-based data. This is widely used, which looks a little bit confusing actually. So we look at this and try to investigate the reason, and we found that the quantifying the airborne GNSS performance using actual flight data remains challenge. Why? Because the airborne the GNSS performance is the GNSS receiver is inside the multimodal receiver, which is the MMR, and the parameters of the GNSS quality from the MMR is not accessible directly to users. There are no, for example, there is no available air-to-ground data links to transmit the measurements or parameters from the MMRs in real time, which means that there's no measurement available. Another thing is that although there is a equipment called a quick access recorder in the aircraft, and the quick access recorder, the QAR, can record GNSS quality parameters from the MMR, but it is not widely installed for all the aircraft, and the data are not publicly available, which means that not everybody can access to the data. As far as we know that only a small part of people, for example, from the administration of the civil aviation department, they can access to this part of data due to the privacy policies. So all this information, all these limitations poses challenges for the investigation of the airborne GNSS performance. Yeah. But we found another way to do the investigation, which is to use the ADS-B. So what is ADS-B? The ADS-B is the automatic dependent surveillance broadcast. So the B means broadcast. It's like a radio. It's broadcast information all the time. So ADS-B is a surveillance technology for air traffic control, which means that the ground air traffic control people, they can monitor the status of the aircraft use the ADS-B. Yeah, so it is surveillance technique. Another point too is that periodically broadcast the aircraft position, altitude, and other status information from the aircraft to ground, which means that the ADS-B will broadcast the aircraft position, altitude, and other status information to the ground, like this figure. So, and the aircraft position is determined by MMR. So if we look at this figure, let me zoom in. Yeah, so we have the MMR installed in the airplane, and the MMR has the GNSS receiver to receive signal from the GNSS satellites. So with the determined coordinates of the aircraft, the coordinates will be transmitted to ADS-B airborne equipment. Then this information will be broadcast to the ground controller. It's like this. So the ADS-B use the data or use the measurement from the GNSS receiver and broadcast it to the ground controller. Yeah. So in the ADS-B message or in ADS-B reports, there are different GNSS-related parameters like the coordinates, which is the position or coordinates of the airplane, which is obtained from the MMR. There's another type of information related to the GNSS performance, like the NACP, which quantifies the horizontal accuracy of the reported position of the airplane, and also the GVA, which quantifies the vertical accuracy of the geometric altitude, and also the NIC, which quantifies the integrity of the position. Yeah, so we can say the coordinates is the position of the aircraft, and the NACP and the GVA is the measure of the accuracy of the position actually, and the NIC is the integrity parameter. And here are two tables. We can say for the NACP for different type of values. So for example, when the local area augmentation system is used by aircraft, the NACP value will be 11. If the wide area augmentation system, the VAS system, is used, the NACP will be 10. So when different service is used for navigation for the aircraft, different value of NACP will be broadcast in the ADS-B reports. Similarly, for GVA, it has 3 different values, 2, 1, and 0, indicating 3 different types of accuracy, actually. So what is the feasibility of airborne GNSS performance evaluation with the ADS-B messages? So this is what we want to explain and what we want to study. The overall methodology. So the figure here looks a little bit complicated. So generally, we integrate the different type of measurements, like the airborne ADS-B data, and also the ground-based measurement, like the geomagnetic field variations, the ionosphere distance measured by the ground receivers, and the position errors of the ground receivers, GNSS receivers, and assess the airborne GNSS receiver performance during the geomagnetic storm. So in this figure, we have 2 different parts. On the left is ADS-B data acquisition process. And on the right is the ground measurement acquisition process, including the geomagnetic field data and also the GNSS data. In the GNSS data, one is the cycle slip detection and also the TC calculation, also the RTI calculation, and then is the positioning error calculation. Yeah. Then the data sets. So So we have two type of data. For the airborne measurements, we use the ADS-B message. A total of over 30 million reports in the southern Canada is used for our analysis. The data is open source data from the Open Sky website. This figure shows the coverage of all the ADS-B data, and the color indicates the sample number. So we can see in some regions the number of samples are pretty high. Actually, this highlights airport in the southern Canada. Yeah. So because the data can have a large area of coverage, so it can reflect regional effects due to the geomagnetic storm. Yeah. For the ground-based measurements, we have two types of measurements. For one is the GNSS measurement. The TAC calculates based on the GPS L1 and L2 phases measurements, and also the ROTI based on the TAC. Yeah. Another type is the geomagnetic field measurements, which can reflect local geomagnetic field variations. So it is can reflect more details in the geomagnetic field variation compared with the global index like the KP or AP. Yeah, and we use the horizontal and intensity component of the geomagnetic field measurement. Yeah, this figure shows the stations we used. Actually, we used lots of stations. For the square, blue square is the geomagnetic station. For the triangle, red triangle is the GNSS station. Yeah, we focus on this region for the analysis. And first is results shows the GNSS responses to the geomagnetic storm. So the storm occurred on the 23rd and the 24th of April of 2023. Because the level of the storm is pretty high and it reached a level of G4. This figure shows the storm period. So in the top panel is the KP value. So we can see from April 23rd to 24th, the KP value is higher. And these two, the panel in the middle and in the bottom is the ASY and SYM measurements, which are the geomagnetic field measurements to reflect the level of the geomagnetic storm. So we can see during this period it is also disturbed or increased, indicating the level of the storm. And on the right panel, on the right of the slide, shows the GNSS response to the storm based on the measurement on the ground. So in the top is the number of cycle slips detected on the GPS L1 and L2 signals. So we can see from the 23rd to 24th of April, there are more cycle slips detected on these 2 days. And in the middle panel is the ROTI values. So we can say higher values are more frequently observed during these 2 days. And on the bottom is the local geomagnetic field measurements. We can see more fluctuations on these 2 days. So this on these slides are all based on the ground-based measurement. And this one shows the NACP and the NIC measurement from the ADS-B report, which is the airborne measurement. So so we first look at the distributions of the NACP and NIC on different days. Just here we can see for the NACP on the top panel, we started 4 different days, 22, 22nd, 23rd, 24th, and the 25th. And the 23rd and 24th are the geomagnetic storm day. So we can see from this figure, there are 2 spikes actually. For spike 9, and there, when the value of NACP of 9, there is a spike, and then is a 10. The reason for these 2 spikes is that in Canada, the aircraft can use 2 different type of positioning services. One is the IceBus, the satellite-based augmentation system. Another one is the SPS, is a single point service. Yeah. So on all of these 4 days, there are 2 spikes of the NACP values of 9 and 10. But on the 24th and 23rd, indicated by the red and orange colors, we can see there is a, on the red colors, we can see there is a decrease on the value of 10, which means that the value, the high value of NACP of 10 is decreased on the due to the geomagnetic storm, and for the value of 10 of NACP is actually for the S-bus aircraft, which means that if the aircraft is using the S-bus service, it is more likely to be affected by the geomagnetic storm. So this is the figure. So on the bottom is the distributions of NIC. So from NIC, there's no obvious variations during the geomagnetic storm day. So which means that NIC produce no difference if there's a storm or not, and if it's for the S-bus based aircraft or single point positioning based aircraft. Yeah. And then is the variation of the NACP and the GVA due to the storm. The NACP is the accuracy of the horizontal positioning, and the GVA is accuracy for the vertical positioning. Yeah. So this figure is a little bit complicated. Let me try to explain. So here, let me zoom in. So here in the top figure, the different color indicates the percentage of different values over all the ADS-B reports. For example, the color blue here indicates the NACP equals 10, and the light green here indicates the value of NACP equals 9. So we can see during the geomagnetic storm occurred on the 24th of April, we can see there are more ADS-B reports with values of NACP equals 9, which means that there are more aircrafts broadcasting the ADS-B message with NACP equals 9. The airborne positioning performance is decreased on this day because a higher value of NACP means a higher accuracy of the positioning. Yeah. And this is for the horizontal one, and for the vertical one, similarly, the value of GVA equals 1 also increases on this die. A higher value of GVA equals 2 decreases on this die, which means that the positioning accuracy with a higher accuracy also decreases on this die. So this is an overall comparison of the NACP and the GVA variation on this die. Yeah. And on the bottom two type of figures. On the left is it's aircraft with the S-bus service. On the right is the aircraft with the single point services. Yeah. So we can see on the left, on the April 24th, there are more aircraft broadcasting the ADS-B reports when it's with NACP equals 9, and less with NACP equals 10. So which means there are more measurements with a lower accuracy on this die. But on the right, we can see, compare with the S-bus based with the airplanes, for the airplane with the single point positioning, the variation is not that obvious. So the accuracy of S-bus service decreases more significantly than that of a single point services. Yeah. And the results also goes to the GVA, yeah, actually. So, oh, sorry, whoops. So, finally, the conclusions and the remarks. So we can say the ground GNS measurements reveal significant increase in ROTI and cycle slip rates during the storm. This is actually obviously and widely investigated. Another thing is that according to the ADS-B report parameters, the GNS positioning accuracy decreased obviously during the storm, especially for the aircraft using S-bus. Yeah. And it is also feasible. Based on our analysis, we found that it is also feasible to investigate the airborne GNS performance using the ADS-B data. Yeah. I also want to mention that the results I presented here is based on the results in one of our publications here, but I only put parts of the results here because the original paper is a little more, there are more results related to the conversion between the different parameters. It's a little bit more complicated, so I didn't show here. If you are interested, please also refer to the article. Yeah, that's all. Thank you for your attention. Yeah, I hope you get some information here from my presentation.
Thank you, Professor Kai Guo. So we will start our section of comments and questions. The YouTube chat. I will turn on my Portuguese mode just to conversation with the public, the YouTube channel. Pessoal, vamos iniciar agora nossa sessão de dúvidas e comentários. Por favor, aqueles que tiverem alguma dúvida, sugestão ou comentário, deixem no chat. Okay, the first one, I saw that Professor Galera left a comment on the YouTube chat, in the YouTube chat, and he wrote, Kai, we just realized test flight in Presidente Prudente. Maybe we can share flight data to test the GBAS implementation from Bingham University and UNESP. What do you think about?
Yeah, that's a very, very good proposal. Actually, in China, how to say, although we have conducted many flight tests, but we haven't tested in the southern of China, where the ionosphere effect is pretty active. So it will be very, very useful if we can share some some results or data to compare the performance in different regions. Yeah.
Okay, fantastic. He also raised a question in the YouTube chat. The question he wrote was, how to compute the accuracy during the flight?
Yeah, this is how to say, this is a very challenging question. So if we want to compute the accuracy during the flight, we need to know the truth of the flight during the truth of the position of the aircraft during the flight. But it is very challenging because when the aircraft in the sky, the positioning accuracy is not really high. So it is difficult to know the truth of the aircraft, the truth position of the aircraft. And so instead of calculating the accuracy of the aircraft, we use the accuracy parameters produced by the airborne multimodal receiver to indicate the accuracy of the aircraft, or accuracy of the positioning of the aircraft. So we just rely on the parameters output by the GNSS receivers to indicate the accuracy. So another way is that, when the aircraft is taking off or landing, the altitude is not high. So we just installed another GNSS receiver nearby, so we can do the post calculation with RTK. So this is validated for aircraft landing and aircraft taking off. But during the en route phases, because the aircraft is too high, it is difficult for us to do the RTK. So this is not realized. Yeah. Okay, perfect. He also left a second comment, a second question for you. From what I understood, the Canadian reports are publicly available. Yes, actually, the ADSB data is available for Canada regions and also for other regions. This depends on the policy of different regions. For example, to be honest, the data for Brazil is not opening because I talked to the surveillance people from Brazil in the International Civil Aviation Organization meetings and asked why the data is not open to public. So, different studies have different policies because the ADS data can reflect the position of the aircraft. It also relates to the security of the country. So to some extent, some countries don't want to share it. Yeah. But for Canada, it is open on the website. If you want to access the website, just Google the Open Sky. You can find the website. Yeah. And you can download the data. Yeah, of course. So we have another comment in the YouTube chat by Professor Leonardo. Professor Leonardo just wrote, "Congratulations on your presentation, Professor Kai. Of the projects currently in development or already completed, which was the most challenging for your group? Why? And thank you." So to be honest, we have in our group we try to develop the avionics for aircraft for navigation and communication. The most challenging thing is to do the test. Actually, we want to do the test of our avionics equipment with the commercial aircraft, for example, from Airbus or from Boeing or from different other commercial companies. But it is always difficult to install the equipment on the aircraft because we need to satisfy many different criteria, like the vibrations, like the how to say, the EMI and the EMC, the interference between different avionics on the aircraft. So it's quite difficult for us. Yeah, I think that is the difficult one. This is a kind of open question. Yeah.
Yeah, it's a tough topic. I will just ask for someone here in person if they have any questions or comments to do. Pessoal, alguém aqui tem alguma dúvida, algum comentário, sugestão que queira fazer para o professor Gege? Okay, no one have nothing to comment or to have, no one have a question for you. So thank you again. I would like to congratulate you. Thank you for your excellent presentation. Do you have any final considerations to do?
Yeah, I want to say many thanks for the invitation, especially to Professor Galera. And so I miss you. I don't know if people in the UNESCO still remember me because I had a short visit here, there in 2018. Yeah, it's quite a long time, but I miss it. And I hope I can visit UNESCO again in very soon. Yeah, and in China it's quite late now, so probably I will drop the meeting and hope to talk to you soon. Yeah, that's all.
Of course, feel free to visit us anyway, anytime, sometime, just if you want. Thank you a lot, Professor Gege.
Thank you. Bye-bye.
Bye. Bom, pessoal, vamos então introduzir a segunda apresentação, terceira apresentação, na real, do professor Demetrios Písicas. Moving on, the third presentation of our Gege Annual Meeting, we would like to invite Professor Dr. Demetrios Písicas to do the presentation. Písicas, make yourself at home. May you have a nice presentation.
Perfect. Thanks a lot for the introduction and also for the very nice presentation before from Kai and the very kind invitation also from Galera. I will also turn off my camera to save some bandwidth. So starting with, so the topic of my talk is really on the multi-genesis, multi-frequency PPB AR. So I want to give you some introduction to the principles and modeling, and then have a look at the evolution, and then on some performance assessment. So hopefully that's interesting for you. So to start with, I would like to really commence with the basic linear measurement model that we use for positioning. So then all of us are aligned. I'm not going into the teeny tiny details, but I want to be sure that we have an aligned understanding. So here you can see that we have a data vector from the user that can contain, for instance, pseudo-range or carrier phase measurements. And then we have a link through the design matrices A and C with the user state vector that, for instance, could include the position, ambiguities, clock, atmospheric parameters, and hardware biases. Then we have a correction vector, and then, of course, a vector that holds the user data noise. Now, it's in all of the positioning techniques, we have these two full rank design matrices, A and C. But in principle, when we take the combined design matrix, we know that this is actually not a full rank design matrix. So we have to take some extra care for that. And what has been done in most of the, actually all of the positioning techniques, is actually to ensure that we can have unbiased estimation of the parameters simply by providing our users with some external corrections. And the external corrections I denote here with #C. And then you can see from the reduced model that now with these corrections, the user is actually able to simply solve for the user state vector elements only. Then the correction error that remains, hopefully it remains very low, so we do not really have to consider it. Now, this is actually the model that gives us all of the information that we need to evaluate the positioning performance based on any technique that we consider. But in principle, we should be looking at the type of the measurements that we use. For instance, if we use pseudo ranges only, or if we also use carrier phase data, then also the estimator plays a role, also the type and the quality of the corrections, and also a very important other factor is some a priori corrections that we need to take into consideration for some local station and environmental effects. Now, before going to PPP, I simply want to start with the standard navigation solution. So really with the SPP concept, the standard point positioning, which is based on pseudo ranges only. The concept makes use of the broadcast satellite orbits and clocks. And of course, the typical estimator is really an epoch by epoch least square estimation. So we do not really take into account any of the dynamic model properties of our state vector elements. And then you can see in the top right that really then the user state vector would simply include our user position and the clock. Now, we have to consider here that the correction error here is not actually very small, it's actually quite significant. And the main reason is that we make use of broadcast products to correct for the satellite orbit and clock. So you see then in the bottom left that by doing an SPP, we see that in the horizontal plane, our positioning accuracy will always be at the few meter level. Now, of course, this is something that we do not really like when we want to go to high precision positioning applications. And then building on top of SPP, I would like to introduce then PPP. So PPP, or precise point positioning, does not only make use of pseudo range measurements only, but it also considers the carrier phase measurements. Then on top of that, we make use of a recursive multi-epoch estimator, and I will explain later on why. Then instead of the broadcast orbits and clocks of the satellites, we make use of precise products. And then also, as I said, we take care of some a priori corrections that we need. Now, you see from the top right that the user state vector now does not only include the user position and the clock, but it also includes the atmospheric delays that are remaining on the user side, but also the phase ambiguities and the hardware delays. Now, the question is, can we really reach RTK level accuracy that you see with the cyan color in the bottom left? So there you see really a positioning error scatter at the few millimeter level. And this is something that we will explore together. But now at least we know for the correction error that because PPP uses typically final products, we know that the correction error is actually quite low, and it's actually lower than the noise level of the measurements that we use. Now, let's dive a bit deeper into PPP, because it's actually both a modeling and a processing method, and I would like really to take each one of the factors individually. So first of all, we make use of both pseudo ranges and carrier phase data, and the reason is very simple. The carrier phase data are actually the most precise measurement. It has a precision that is 2 orders of magnitude better than the pseudo ranges. Now, what you see then on the plot is actually not commensurable. What we see is actually a positioning error at the few meter level. And the main reason is that we simply make use of an epoch by epoch least square estimation. And in such a simple model, with such an estimator, we do not allow actually the phase data to contribute to the position solution. And the reason is simple, is simply that as many phase measurements as we have, then as many phase ambiguities we do have. And in this sense, the phase data do not really contribute to the position solution. But what would happen, for instance, if we move on to a recursive multi-epoch estimator, and in this case, we can actually make use of the time constant property of the phase ambiguities. Now you see a completely different picture. We see now that we are at the few decimeter to meter level performance, but you still see that our error is not really at the centi or millimeter level. Now, one of the reasons is quite simple, is that I was using before the broadcast orbits and clocks, which have a quality level at the meter level. But if we then use the precise products, so then we do not contaminate our millimeter level precise phase data, what you see now is that along the east and the north components, so really the blue and the red curves in the figure, you see that they're really zero mean. Of course, there are some oscillations at the few centi or decimeter level, but then we see that the up component, although it shows some precision, it's not really accurate because you see that it's really biased. Now, the main reason for this is actually that I was not considering before the local station and environmental effect corrections. And these actually contain quite a lot of corrections that have to do, for instance, with antenna phase center corrections, also the relativistic clock correction and the Shapiro effect, but also tides, troposphere and phase windup. And then you see that by considering all of the 4 different factors, then our positioning error across all of the components is really at the few centimeter level. So I'm not sure if you can see on the screen, but the repeatability for all of the components is at the millimeter level for the east and the north, and then at 1.3 centimeter for the up. So this is nice. So by considering all of them, we can actually be at the few centimeter level. Now, let's have a look at the convergence time, because we saw that we can reach the millimeter level, but can we actually reach it very fast as it happens in RTK? We know that PPP solutions actually experience a long convergence time. And as you can see then in the graph, what I have plotted here, so with all of the gray curves, you see individual solutions, okay? So I computed many bi-hourly positioning solutions across a day. And then to really have a proper statistical metric, I simply take the 95th percentile. And as you can see from the red curve, you see, for instance, that the float PVP solution takes more than 30 minutes to actually reach the 10 centimeter level. So we can reach the millimeter level, but still we require quite a lot of time. Now, 2 are actually the main reasons. So the first one is, of course, the anospheric delays, because the user needs to estimate the slant anospheric delays. It's one of the parameters that lie on the user state vector. And unfortunately, we do not really have available precise models to correct for that. Now, the main second factor is actually the phase ambiguities, because by simply using the single receiver user phase data, there is not sufficient information to really resolve the integer phase ambiguities. Now, I will explore a bit this second factor because it's one of the important ones. And what I mean is that by simply using code and phase data and satellite orbit and clock products, then the PPP-based phase ambiguities are not integer anymore. And the main reason is that there is a specific term, like you see on the top left, that is called the satellite phase bias term. And this actually contaminates our integer valued ambiguities. And at the end, what the users actually estimate is the real valued phase ambiguities. That means that without any additional corrections, we are not able to resolve the ambiguities, hoping that we can exploit much earlier the contribution of the very precise phase data. Now, what we can do now, what is actually very attractive is, okay, can we somehow synthesize a concept that at the same time exploits the single receiver properties of PPP, but at the same time to use the advantages from RTK, that it's also at the centimeter level, but it has the capability to actually resolve the phase ambiguities and go to the millimeter or centimeter level. Now, these 2 concepts depend on the different correction types. So we use state space corrections for PPP. So we use orbits, clocks, bias, and ionospheric or tropospheric corrections. But then in RTK, we actually make use of observation space corrections, so really OSR corrections. Now, these 2 concepts are very similar and very different at the same time. And as I explained before, PPP has a very long convergence time, but at the same time, it has this very attractive feature of really being able to do global positioning without any explicit dependence on reference stations. And then on the other side, we have RTK with very rapid convergence because we can actually integer estimate the phase ambiguities. But unfortunately, this we can only achieve in short baselines, meaning that if we start moving to medium and even long or very long baselines, then still ionosphere is one of the limiting factors. Now, can we somehow merge the two concepts? Now, I want to start from a general measurement model to explain you how we ended up to this combined concept. So let us now take the assumption that we have a central processing facility that we can actually collect the measurements from both the network stations and the user stations, okay? So you see on the left that I have a vector of the network measurements and then a vector of the user measurements. And if we stack them together, we're simply able to solve for any network-specific parameters, for user-specific parameters, but also for the vector C that, as I showed you in the very first slide, is the vector that holds the estimable forms of all the satellite-related corrections. Now, if we actually take the weight matrix as the inverse of the measurements variance matrix, we will actually end up with a minimum variance solution, because the minimum variance property is the optimality criterion that I use here. So that means that if we do a jointly square adjustment of the network and the user data, we actually have the best possible user positioning solution. And this is what we call the in-loop user. Now, although this sounds very nice and very attractive because it's the best possible positioning solution that we can achieve, this actually is a very costly approach, both from a computational point of view, because you can imagine that we need to collect all of the measurements at the same processor for all of the different users that need to get the positioning solution. But at the same time, we have a data transmission problem, because all of these data need to be collected at the same processing facility and do all of this parameter estimation. Therefore, what we do, we simply split this approach in two different steps. So the first step simply considers taking the network measurements to estimate for the network-derived state space corrections, and then taking these corrections to the users, meaning that any user can make use of these corrections and actually get the estimate of his own parameters. And here I come to the OSR vs the SSR concept, because it's two concepts that differ but are also very, very similar at the same time. And the network RTK approach is really the one that depends on the observation space corrections, but PPP RTK, which is the correct terminology for this concept, makes use of the state space corrections. Now, of course, we need to take into account that all of these corrections can be transmitted with a different update rate, meaning that we have a latency on the user side that needs to be taken into account. And of course, any covariances or time correlation between measurements or even corrections should not be ignored, because if they are ignored, then we will not be able to end up to optimal user parameter estimation. And that's why I simply make the remark here that the network corrections are simply a good approximation of the optimal solutions. Now, moving on, we all know that network RTK is able to perform within a few tens or maybe even hundreds of kilometers through the VRS or the MAC approach, simply by making use of corrections in the format of original GNSS data. And then the users can simply take any single and even double differencing operations to really take advantage of the residual atmospheric information between all of the different multiple reference receivers. Therefore, that means that if OSR actually works, why do we need to go to the SSR and to the actual PPP RTK concept? Well, the reason is actually very simple, and I think I gave the hint before. It's that really all of the state space corrections, they have their own temporal behavior. So, for instance, we have the satellite orbits that smoothly change over time. Then we have the satellite code and phase biases that are actually very stable over time, meaning that they simply need a very low update rate. But then we have the satellite clocks that we know that not only they change very rapidly in time, but we also know that they change randomly. So to really accommodate some high precision positioning applications, we really need high update rate. And this is actually the flexibility of the SSR corrections that we use in PPP RTK. Now, moving on, you can see here a graphical representation of the PPP RTK concept that is actually also used for the PPP AR. Actually, in literature, these two terms are used interchangeably, but in truth, it's the PPP RTK concept that is the correct terminology, and PPP AR simply means that we do not make use of any external atmospheric information. And in this sense, we could simply call it an ionosphere float PPP RTK. So what we see now, again, graphically, we have a network collecting the measurements from satellites, computing the SSR corrections, transmitting them, of course, each one with their own update rate. And then the user can simply take all of these corrections, apply them to the code and the phase data. And at the end, what you see at the top right equations, very simply, is that the user phase ambiguities would simply end up in a double difference form. And this is actually happening by the phase biases corrections that are being provided by the network correction provider, but at the same time, also by a datum parameter that the user need to consider to resolve the rank deficiency between the receiver phase biases and the phase ambiguities. That means that if we have double difference ambiguities at the user, we actually have integer value ambiguities that we can simply resolve. And then, of course, if we make additional usage of atmospheric corrections, we can have the full PPP RTK concept at hand. Now, this was nice. I think I gave you the good setup that we can now really go to more numerical stuff. And what I did for today's presentation, I simply took 4 receivers in Australia that you see also in the graph. And I processed GPS dual frequency and also Galileo triple frequency code and phase data. I exploited the uncombined and the undifference observation model so that really all of the information exists in my model, so then I can take any constraint that can be used to augment the network solutions. And then all of this, of course, was estimated within an integrated network data processor that makes use of a generalized Kalman filter. And what comes out of it is really the clocks for both the receivers and the satellites, also the satellite phase biases that we need for PPP AR and PPP RTK. And also, we're doing network ambiguity resolution using the lambda approach. Now, I want to start with the phase biases, because I'm not sure how many of you really have a sense of what these parameters are. And as I told you before, these are really hardware delays on the satellite end. And as I said before, their behavior is really constant over time, or let's say almost constant. So what you can see now in this slide is really the satellite phase bias estimates for GPSL1 and GPSL2 on the left and the right respectively over the entire day that I selected. Now, each color actually represents a different satellite, and what you can see is that really these phase biases, once estimated, you see that they remain constant over time. So they really take quite some precision over time. Now, I simply took these phase biases and I started really with a GPS dual frequency scenario, making use of kinematic PPP AR. And when I say kinematic, I mean that we do not take any assumption on the user mode. It means that the user positional parameters are assumed to be completely unlinked in time. Now, what you see is actually the positioning error over time for the float mode on the left and then for the fixed mode on the right. Now, what you see, for instance, is that the main difference is at the very first hours. So in the very first hours, in the left, you see the float PPP solutions that really require some time until they go to the 10 or even the 5 centimeter level. But then they actually oscillate around the 0 value, but of course with a certain uncertainty. But then if you go to the right with the fixed solutions, you see that despite some wrong fixing, because if our model is very weak, because this is actually a very weak model, we have a GPS dual frequency model where we also estimate the atmospheric slant delays. So it means that our model is actually very weak in terms of the ambiguity resolution capabilities. And instead of this wrong fixing, then you see that after some time, actually our positioning error drops significantly and immediately to the few centimeter level. And even from the repeatability metrics, from the standard deviations, you can see that it really drops from the 4 and 5 millimeters to the almost 2 and 4 millimeters again, and also an improvement along the up. But again, the improvement is not really significant for the accuracy, because at the end, the dynamic model that we use for the phase ambiguities will allow also the float solution to actually reach the same performance level. It's only the convergence time that really is what matters here. Now, in this slide, I also show you the 3D positioning error to actually see that more clearly. And then you see, for instance, the float solution with the blue and the fixed with the red. And you see that, of course, they have a different convergence time. So really, it takes a different time for both of them to reach the few centimeter level. But after convergence, you actually see the 3D error of both float and fixed to be more or less the same, which is actually something that we expected. Now, this was for the let's say, for the accuracy, but to really have a sense of our convergence, we again need to run multiple positioning solutions and then see really in a statistical point of view where we stand in terms of convergence. Now, this is what I did here. On the left for the float solutions and then on the right for the fixed solutions, and both of them refer to the horizontal component. So what you can see now with the red color is really that the float solution takes more than 35 minutes to converge to the 10 centimeters, but then with the fixed we see that it takes less than 25 minutes to actually converge. So we already see the improvement in the fixed solution. And again, you see some wrong fixes. And by wrong fixes, I mean, for instance, some jumps in the positioning errors that indicate, of course, that we have a weak model, so ambiguity resolution cannot be successful within a very short time span. So it's good news, it's 25 minutes, but is it really enough? Is this something that can compare to RTK? I think it does not. So let's now move on and see how we would be able to augment that, how we are able to strengthen our user model in such a way that the convergence time can be reduced. This we can actually achieve it by increasing the number of the involved satellites and frequencies. This means that by including more constellations and more frequencies in our model, then we can really augment it. And what I simply do, and you can also find it in our publications, we simply extend the single system model formulation to a multi-system one in the same way, with the difference that we take system-specific clocks and hardware delays. So we do not really make any assumption on a common clock across the GNSSs or across common biases, for instance, for some overlapping frequencies between the constellations. And the only point that needs to be addressed here is that when we go to the multi-frequency applications, then the users need an extra correction. So they do not only need the satellite orbits, clocks, and the phase biases, but they also need the code biases for any frequency that goes beyond the first two. So this is what we call in literature the non-pivot frequencies. Now, let's now have a look at the combined solution, so really GPS and Galileo dual frequency. I did the same experiment as before. So what you see again in this slide is the float individual positioning solutions on the left and the fixed on the right. And again, with the red curve, you can see really the fixed. Now, what you can see now is that we have a much better convergence time. So even for the float, the solution can converge to the 10 centimeter level within 7.5 minutes. And then if we fix the phase ambiguities, within 4.5 minutes, we can converge to the 10 centimeter level at 95% of the time. So this is actually very good news. So this is nice. And let us now make the transition to a multi-frequency approach. And before doing that, this slide is simply here to show you really how the behavior of the satellite code bias estimates looks like. So in this case, I consider the E6 frequency of Galileo as the third frequency that I make use of. And of course, we need satellite code biases. And this is an estimate that comes from the network estimation part. And you see that after some initial epochs for every individual satellite, then the satellite code bias estimates, they actually remain quite constant over time. Let's now move to the triple frequency PPP-AR, again with GPS and Galileo, and then doing the same statistical analysis, we see that the float convergence time at the 95% remains the same, but then on the fixed, we actually have an improvement. We see that the convergence time to the 10 centimeter level takes actually 2 minutes only. So it means that within 2 minutes, we're able to reach a sub-decimeter level simply by exploiting multi-constellation and multi-frequency measurements. Now, the main reason that we have this augmentation with the additional frequencies is actually the frequency separation that plays a significant role in integer ambiguity resolution. It is a common misunderstanding in literature that the more frequencies one uses, the better, but it's actually not the number of frequencies that plays a pivotal role. It's actually the frequency spacing. And this is what I also have done in one of my publications, that you can see one of these graphs in this slide. And what I have plotted here, for instance, is the formal ambiguity success rate as a function of the selected third frequency. And you see that once you select two main frequencies, let's say the two pivot frequencies, so in this case it's the E1 and the E5A, then the more away you move from these frequencies, the higher the ambiguity success rate becomes. So that's why the E6 is actually the one that brings the highest contribution. If on top of this, you add E5B and E5, you will not actually see any improvement in the convergence time, but of course, it brings improvement from a resilience point of view. So we have a redundancy, which is always important when we are in high precision positioning applications. Now, we saw that we can actually achieve very rapid convergence times, and this is actually very, very nice. So we see that from an accuracy point of view, we can match RTK. From a convergence point of view, we're almost close. If you actually include more constellations like Beidou, GLONASS, and QZSS, literature has shown that we can be really almost instantaneous convergence-wise. But then there is also another point that is somehow overlooked in literature, and this has to do with the reliability aspect. So actually, PPP-AR is a very nice concept for real-time positioning applications, but we need to consider that these corrections are transmitting with a certain update rate. I think I highlighted quite many times as part of the SSR concept description. So that means that if there is an update rate, that the users actually experience some latency. And this you can somehow understand from this graphical concept that I have put in the slide. So what you see, for instance, is the timeline for the network correction provider and the user. And then for each of the red dots that you see for the provider, it's actually the time instances that the provider is making available some corrections. But of course, the user would have a higher rate of measurement. So in this case, for instance, you can make the assumption that we have a user with a 1 second data, and then a provider is simply providing the corrections with a 5 second update rate. So you see that over time, we have a latency until the user is being provided with the next correction pack. Now, what happens? Going back to the general measurement model that I introduced in the very first slide, you see that the correction error, which now actually becomes a correction prediction error, because the users actually need to predict in time their corrections to make sure that they're applicable for the user positioning time. And this prediction error can actually increase quite significantly. This means that if it increases in such a considerable way, we need to take this into consideration. Now, unfortunately, what has been done in the classical PPP-AR literature is that the stochastic model of the user-corrected pseudo-range phase data is actually equal to the stochastic model of the uncorrected data, which is actually incorrect. One should really take into account the uncertainty of this correction prediction error, and I will explain you why. The main reason, the main outcome that we will see in the following slides is really that, first of all, since we have a misspecified model, we already know that we will never achieve the minimum variance parameter estimate solution. We will always end up to suboptimal parameter estimation. And of course, there is an additional effect that the confidence interval, so really the positioning confidence that is being given by our model, will stop really being trustworthy. Let's have a look at the results. So what I have been processing here is a kinematic GPS dual frequency scenario, again using PPP-AR. You see the ambiguity float solution on the left and then the ambiguity fix solution on the right. Now with a black color, we can see the positioning error across the different components. So east on the top, north in the middle, and up on the bottom. And with the red curve, you can see the 95% confidence interval that is being directly given by our Kalman filter. It means that this is simply the square root of the elements of our positional covariance matrix that comes from the Kalman filter. Now, what you see here is that actually the confidence intervals after convergence, they can bound the positioning error, but it's not really completely. Now, the setup in this case considers that we collect data every 30 seconds and also that the corrections are being provided also every 30 seconds. So it means that the users do not experience any latency, but still the correctional uncertainty is usually ignored. And the reason is very simple, because imagine that you already transmit quite a lot of corrections to the users, and to transmit also the error variance covariance matrix of the corrections is actually quite costly in terms of transmission point of view. Therefore, what the classical PPP AR community is doing is simply ignoring this uncertainty. But what you can see that in both the float on the left and the fixed on the right, you see that in the very beginning, the positioning error is not really completely bounded by the confidence intervals being produced by the filter. Let's now move to the case that the corrections are not being provided with every 30 seconds, but they have been provided with a 90-second update rate. So this means that now the user will experience a latency in the corrections that will range up to 60 seconds. Again, we ignore the correctional uncertainty. And then what you can see, first of all, you see that the positioning error for both the float and the fixed solutions, actually it's more noisy. It's quite more noisy. So we see that from a millimeter performance, we really go to the centimeter performance. Actually, if you check on the right, you see many spikes on the fixed, which could actually go even above the 20 centimeter. And this can be explained very simply. The main reason is that once we have this correction prediction error that we do not take into account, this is simply contaminating our phase data. So we have more noisy phase data. And of course, once we resolve the phase ambiguities, this will we directly observe in the positioning solution. And this is what happens. But again, you see that we can achieve, for instance, very high precisions. But what we additionally see is that the confidence intervals actually do not bound anymore the positioning errors because we do not take this uncertainty into account. Now, let's have a look at what happens once this correctional uncertainty is being taken into account. So now what I have been doing, I have been considering also the correctional uncertainty that is being estimated by the filter itself, but I'm also taking advantage of the dynamic model of the network at the user side, so then the user is able to time predict the correctional uncertainty. And now you can see, for instance, from the black curves that the positioning errors are actually smaller than before for many, many different cases. And this is an effect because now we do not have anymore a misspecified model, or let's say an almost correctly specified model, and I will explain why. But the nice thing is that the confidence intervals actually now very well bound the positioning error. So we see that now we can have some positioning trustworthy, some positioning confidence there. But I know that it's not very well visible. So what I did, I made a zoom in the very first hours to also show you how the correctional latency plays a role. So you see now, for instance, for the positioning error, that over time you see that it increases and it's coming back to almost zero, then it increases and is doing all of these zigzag behaviors all the time because the latency is simply going from 0 to 60 and again to 0 to 60. So all the time we have some residual correction errors that are small at the zero latency and of course increase as the latency increases. But again, we see that the confidence intervals for both the float and the fixed positioning solution actually can bound them. And this is very important because then it means that not only we have accurate and very rapid PPP AR solutions, but we can also have trustworthy positioning solutions. Now, this was for GPS only dual frequency. Let's now go to the GPS plus Galileo triple frequency solution. So really the most strong solution that I showed in this presentation. Now, of course, you see, again, two things. So the first thing, as before, is that the confidence interval can very well bound the errors for both the float and the fixed solution. But what is now striking is actually the errors are much smaller. So what we see now is that although the user experiences some latency in the corrections, then by simply making our model stronger, then this also is being reflected in our user positioning solution. That means that by strengthening our model, then we can somehow alleviate all the effects that are being brought by this correctional update rate. Now, I said before that we have an almost correctly specified model, and the reason is that although the corrections have some uncertainty that, as I said, can increase over time due to the correctional update rate, but we also need to consider that all of these corrections are being estimated on the network processor with a Canal filter. And this actually means that the corrections do not only contain some uncertainty, but there is also time correlation that is being there. And that means that by making use of time correlated measurements in the Canal filter, we violate one of the standard assumptions, and then that means that recursive minimum variance estimation is not possible anymore. And to visualize this to you, I have computed the formal time correlation for different latencies in this graph, and then You can see, of course, that the longer the latency, so the more that you go to the purple color, of course, the smaller the time correlation. But again, it's important, for instance, for any of these. So it means that it may decrease over time, but time correlation will always be there. And of course, it plays a role on what is even the data sampling period, because now, for instance, I used only 30 second sampling period for the GNSS measurements, but you can imagine that by using 1 Hertz measurements, it would make this quite more strong. Now, can we really find a solution to this problem? Can we really find a solution that can handle this time correlation and the uncertainty of the corrections? Actually, there is a solution, and we have developed a new addition of the generalized Kalman filter. So instead of doing the classical measurement update, what we now introduce is another generalized Kalman filter variant that instead of doing the measurement update on the user parameters, we also have the correctional update. So that means that we do not actually correct our measurements anymore, but we simply take the network-derived corrections as pseudo-observations at every instance that they're being provided until they're being provided again. And then we can solve the time correlation effect to a very large extent. We actually do a joint time update and measurement update for both the user state vector elements and for the corrections that are being provided, but still lie in the general measurement model that I also showed in the very first slide. Now, does it actually solve the problem? So what I show you here is one of the test cases that we have been, we published quite a few years ago. And the main comparison is to be done between the blue and the red curves that you see on the 3 plots on the right. So really the east arrows on the top, the north arrows in the middle, and the up arrows at the bottom. And what you see now is that, as before, these blue curves, which only consider the uncertainty of the corrections but not the time correlation, you see that we have this increase of the error over time, and then they drop again to smaller values, and then they again increase. So we have this seesaw behavior of the error. But once we make use of this new Kalman filter variant, you see that this is very much alleviated. So you see that now we can achieve smaller positioning errors, which is something that we like, meaning that now we can have an almost correctly specified model, and then this of course augments our reliability outcomes. So coming close to my summary, I think that these are the takeaway messages that I would like for you to get. So first of all, with multi-constellation, multi-frequency PPP-AR, we're actually able to obtain RTK performance levels in terms of both positioning accuracy and convergence time without making use of any external atmospheric corrections. Then, of course, to be able to get the optimal parameter solutions for the user in the sense of obtaining the minimum variance solution, we need to correctly specify the underlying model. And although here I made a large remark on the stochastic model, because this is actually the one that's being overlooked in literature, the correct specification also considers the functional model, because we also need to make sure that there are not any mismodeling biases that may contaminate especially our carrier phase measurements. And of course, in the case of latency, so really in the presence of any correctional update rate, then we need to be sure that we take into consideration this uncertainty of the large correction prediction errors, because as you saw, it can affect the ambiguity resolution process. So then indirectly, it affects the positioning accuracy and the convergence time, but at the same time, it affects also the reliability outcome. So really the confidence bounds that we get stop really being representative once we misspecify the model that is being used for the user parameter estimation. Now, of course, I also delineate some very nice topics that I hope that some of you could actually investigate in the future. And also, if you need any more brainstorming, I would be very happy to discuss individually with you. So some of the very hot topics in the PPP-AR domain are really the integrity concepts, as I said, because in most of the integrity and safety of life applications, you will see that really this correctional uncertainty is not being taken into account, although it should. Then, of course, the PPP-AR concept has been studied in urban environments, but of course, we need further research for these GNSS challenge environments, because I think I made a very clear conclusion that more satellites and more frequencies are important, but really in urban areas we're not really able to have so many satellites visible, so we really need to find some optimal ways to tackle this issue. Then, of course, we have the very hot topic of the low-cost mass market data coming from either smartphones or smartwatches, and really being able to optimally exploit them, and even to avoid any of these mismodeling biases that exist in the smartphones. Then, of course, is the ionosphere modeling. That is one also of the very interesting topics. I have not addressed it in this presentation. I think I did this a few years ago for the seminar, but it's one of the very interesting topics, and especially flexible ways of disseminating the ionosphere. This is especially important. And of course, one of the critical points is to consider PPP-AR as one of the core points for really doing, for instance, autonomous driving. But again, it's simply a part of a sensor fusion solution, because GNSS cannot be used as a standalone system for localization. We need really to combine it with other sensors. But again, we really need to make a very good merge of all the different sensors and the data to obtain good positioning solutions. Now, before concluding, I would like to make you aware of a very recent Springer book that me and many other colleagues contributed to. So this is an anniversary volume that was really published in dedication to Professor Peter Tennyson, who actually very recently retired. So many of his previous former PhD students, but also current collaborators, contributed with individual chapters. So these are really self-contained chapters that you can have a look to. And the chapters span many different topics, going from geodetic estimation theory, advancements in GNSS, LEO-based navigation, because this is also a very nice topic. So really exploiting low Earth orbit data for PPP-AR and high precision positioning in general, but also, for instance, terrestrial positioning applications through the super GPS system. So that was it from my side. I hope that it was interesting. If you have any question, please let me know. And you can also contact me individually if you want to discuss further on any topic. Thanks again.
Thank you, Dimitrios. Congratulations to your excellent presentation. We have some in-person questions right here in UNESP. So we will start the comment section with a question by Professor Paulo Sérgio from UFPR, nowadays at UNESP. Professor Paulo Sérgio, feel free to make your question.
Hello, Dimitrios. Here's Paulo. I would like to congratulate you for a nice presentation. It is a very interesting topic, and you showed very nice results. And I would like to know from your experience, how often an ionospheric model needs to be updated for PPP-AR purposes?
Paulo, thanks a lot for your question and the remark. Actually, this is a very interesting topic. Of course, there is not any conclusive answer to that, as you understand, because it really depends also. I mean, let's say that we have a correction service provider that may transmit, for instance, an ionosphere product, so maybe they will simply consider only, for instance, how much the positioning performance may degrade, for instance, because then we need to take into account how much really the ionosphere changes during the day, during the night, if we have some solar geomagnetic storms. And this is not a very easy topic to be taken into consideration once you really establish such a correction service provider, like, for instance, the Galileo High Accuracy Service, with actually within its phase 2, it will also transmit some atmospheric corrections. And there has been some detailed analysis on what should be, let's say, one of the optimal update rates. Unfortunately, I cannot comment it during this presentation because it's not public information, but from my own experience, ionosphere should not really have, let's say, a low update rate. In my consideration, if the purpose of the ionospheric product is to augment PPP-AR convergence, then we really should talk for medium to high update rates.
Okay, thank you very much, Dimitrios. I'll take note from your response.
Thanks.
Okay, so let's move on for our second question here in person from Emmanuel Gomes from UNESP Prudente. Emmanuel Gomes, feel free to make your question.
Hello, Professor. I'm Emmanuel Gomes. I'm a PhD student in UNESP. I've been investigating for my thesis about the estimate of STC, okay, slant total electron content, through the constrained coordinates, considering the PPPAR uncombined and undifference model. So my question is, what do you think about the possibilities and challenges that you consider in this case, in this scenario? And also about the parameters, what do you consider the most important? Could be 1, 2, 3 of them. This is my question. Thank you.
Thanks a lot for your question. So as far as I understood, you make use of a PPP fixed model. So you take the positional parameters as fixed, or some constraints, maybe from a SINX file or from any daily static solution. So you use a very strong model to estimate the stack, so really the slant atmospheric delay. Now, this is possible. This is something that I have also been doing during my PhD research. One of the significant remarks that I want to make is, if you really want to get some representative ionospheric delay estimates, one of the important things is really the assumptions that you take as per the temporal behavior of the ionosphere. So usually you see, for instance, in literature that most of the researchers, they assume, for instance, a constant state random walk model to take into account, for the temporal behavior of the iono, with usually some arbitrarily selected spectral densities. Now, this may work in several cases, but if, for instance, your research focuses on some more intense, let's say, ionospheric activity cases, then my proposal would be to simply consider the ionospheric delay states as completely unlinked in time. That means that you make use of the generalized Kalman filter that we developed with Professor Peter Tennyson, and it has the flexibility that your filter does not need to have a dynamic model for all of the involved parameters. So this is actually a quite nice approach, because you do not need to take any assumptions. So whatever you do, you know that the delay estimates that you get are more or less representative, because any of the variations that exist in the ionosphere will simply be mapped to your state estimates. But if you somehow misspecify your dynamic model, it could be that some of the actual ionosphere is going to the S-stick, but some of it, for instance, may go, I don't know, maybe also to the phase ambiguities. So this would be a remark from my side for your research. Did I cover your entire question, or is there something that I left out?
Okay. Thank you. Thank you a lot.
We have many questions by Professor Galera on the YouTube chat, but we don't have a time to answer this question, to ask this question. We only have a time to ask one question from Felipe Tintino from NESP. He wrote in the YouTube chat. Dimitrios, how to link the error with the formal precision that normally is quite optimistic?
Yeah, it's one of the topics that is very interesting, and I have also been personally investigating during the last few years. So the way really to move forward in ensuring that the formal precision that you get matches the positioning error is simply to really consider the uncertainty of the actual dispersion of your measurements. So it's like the slide that I showed, if I can go back. So it's really everything in this slide in the bottom right equation. So really the stochastic model of your user corrected measurements really needs to capture the actual uncertainty of your measurements. Usually we simply take only the code and the phase noise, but this correctional error needs to be taken into account. Unfortunately, this is not, for instance, a product from the IGS. In my case, I have my own processor, so I'm able to get this correctional uncertainty and do this research. But then, of course, one can also do this, let's say, empirically. So once you get some real-time corrections, you can simply make some empirical error evaluations with some ground truth products, like the final products from IGS. And then you can come up with, let's say, the empirical covariance matrix that you can use. Now, what we showed in our research is actually the component of the stochastic model that plays the most significant role is the one related to the corrections dynamic model. So really the error variance covariance matrix that comes from the network, you do not really need it, but what you actually need is all of the information that resides in the network's dynamic model. So then on the user side, you're able to make use of the time prediction for the system noise. So this is very important. If you want to get some further information, please send me an email, and then I can really direct you to some of our publications that we really tackle this issue.
Perfect. If you want to see the other questions by Professor Galera, you can see in the YouTube live chat, okay?
Perfect.
And
Thanks a lot.
to answer, just if you want. You have any final considerations?
No, I would like to thank the entire organizing team and also Galera, and I will make sure that in the next seminar I will present on site also to meet you in person.
Okay, so I would like to thank you again. Congratulations
Thanks.
for your excellent presentation. I would also like to thank you to the more than 50 people watching our live stream, both in person and in YouTube channel. I would also like to invite you to check your attending on our attendance list. I will just talk a bit in português. Pessoal, se vocês quiserem assinalar a sua presença, nós estaremos deixando aqui na nossa tela um QR Code na qual vocês podem apontar o celular de vocês para deixar a sua presença confirmada. Lembrando que esse QR Code vai ter a validade até o final dessa transmissão ao vivo. Então, por favor, fiquem à vontade para apontar a câmera e assinalar a sua presença. Moving on for the next presentation, I would like to invite Professor Benedict Soya. Professor, may you have a nice presentation and feel free to do your presentation.
Hello, and thanks a lot for the invitation to present here in this great event. It's really a great pleasure to speak here along such great speakers like those before me. Really exciting presentations, and also really a great community that we have here in terms of geodesy and navigation challenges. And yeah, today I would like to focus on also a rather novel aspect in that ecosystem, namely what the impact of AI will be on geodesy and geodetic Earth observation in the future, and what are the different perspectives. So in general, just a very brief background where I'm coming from and what my major steps have been in my career. I've done my master's studies in geodesy at the Technical University of Vienna, did my PhD at GFC Potsdam, the Geoscience Research Center there, postdoc at NASA Jet Propulsion Laboratory, and then finally I came to ETH Zurich, where I'm currently also located, and where I had the great opportunity to establish a new research group on space geodesy. Now, this group, the Chair of Space Geodesy, exists now since almost 6 years. And our focus has been really to apply machine learning and AI in many different challenges in geodesy. And in terms of data, we are really interested in using GNSS, which is very versatile and has many different applications. Based on my own background, I'm coming from VBI, a very long baseline interferometry, so I'm also really interested in that. And then also really important for Earth system monitoring, satellite gravimetry, because it can really tell us a lot about the climate and mass distribution in the Earth system. And in general, I really wanted to establish a global community to focus also on AI in geodesy. And through the Global Geodetic Observing System, GGOS, I had the opportunity to establish a so-called focus area where different people can come together, exchange ideas, and collaborate on certain topics. And I'm really grateful that the GGOS executive board decided to let me establish this focus area on the topic of AI for geodesy. And I'm doing this together with Maria Casalini, and also we have some subgroups which are covering different topics also led by several other people. So of this focus area, the main goal is to develop and evaluate new geodetic data and products using AI and machine learning, both in terms of achieving higher accuracy, higher temporal or spatial resolution, improving the prediction quality and real-time capabilities, and also really important, I think, make everything trustworthy and interpretable, especially with the more complex machine learning algorithms. This might be quite important, I think. And so far, we have already more than 100 members. So if you're interested, please let me know. And I would be happy to also have you on board in this initiative. Now, AI is now really, I would say, the technology that is shaping our lives at this moment. And just very recently, the Time magazine has really selected AI, or the people behind AI, as their person of the year. And you can see here all these big tech company CEOs that really are building these large models like ChatGPT, and the equivalent versions from companies like also Google, XAI, and so on. So AI nowadays is really everywhere, like in many companies also, and can be used for so many different tasks in language, images, video, and so on. And also really in sciences, it has been also become a major factor and driving force. For example, last year, the Nobel Prizes, they were really related closely to the sciences. Like there was a Nobel Prize in physics related to neural networks, and then also in chemistry, where the Nobel Prize goes to people that developed AI methods to improve the protein structure predictions. Actually, some people related to Google. And that has been really a common trend or overarching trend, that AI is really useful in many different scientific disciplines. And that has actually not only been done at universities, but really also by big tech companies like Google, NVIDIA, who have really invested a lot of also money in developing new scientific models using AI, for example, in applications of medicine, health, chemistry, what I mentioned, this AlphaFold, which is used for protein structure, and also really very close to geodesy, also for Earth system modeling, and in general, Earth models, representations of the Earth, using Earth observation data, atmospheric data, and so on to improve our understanding of the climate and also provide better predictions. So here in this regard, really one of the best Earth system models right now is Aurora, developed initially by Microsoft, and also for the geospatial information. Alpha Earth is really very promising. That is based on a multitude of different Earth observation data sets. Now, really the type of algorithms and models that are used by these very mature models are very refined already. So in principle, it's based on models that have been developed, or the technology that has been developed some years ago. And of course, it's still somehow refined, but really the limiting factor has always been the amount and the quality of the data. Since also for these big companies, just the computation is not such a big limitation anymore. There are now really very large supercomputers that can take care of all this data that is out there. But without the amount of data and really the quality of the data, you would not be able to create such really game-changing AI models. And now that's where I think also in geodesy, there's a great potential. Since in geodesy, we are also relying heavily on data for our purposes collected by satellites. So, based on observations done by satellites. So we have a global coverage and many different types of data just listing here, for example, GNSS, where we can basically, since it's a passive technique on the ground, we can just install more and more stations and get more and more data. It's very scalable. And of course, also, INSA, where more and more missions are coming that are going to produce like at the order of petabytes per day in the future. Altimetry, of course, also, and gravity measurements from satellites also. So a lot of different kinds of data sets that are out there characterizing our Earth, and which are really useful, especially since they are typically of very high quality. So in terms of GNSS, for example, we can say that we can determine the positions of these permanent reference stations really at the millimeter level, where we can really then resolve really small signals that are related to the Earth system, like changes in the atmosphere or in the hydrology around the station, or seismic deformations, tectonic movements, and so on. So a lot of opportunities. And even better if we can combine the geodetic data also with other data sources like auxiliary data, like weather models, climate models, environment models, and so on. So I would say in terms of data, actually in Geodesy, we are very lucky, also since most of the data is also openly available and not really confined to individual countries. Now, in this talk mainly, I want to, first of all, give you a very brief introduction just to the basics of AI and machine learning to bring everyone to the same page. Then I will have some examples that I want to mention based on existing research in the field of GNSS for atmospheric monitoring, then using satellite gravimetry, like the GRACE mission for mass changes monitoring, and then also for Earth orientation parameter prediction before I wrap up with an outlook on the future in AI for Geodesy. So let's get right into it. AI and machine learning. So what are we basically talking about? I've now thrown around quite a lot of terms like AI and machine learning. So what's basically the difference? So, I mean, in principle with AI, we are talking about techniques that basically enable machines to mimic human intelligence. So that's very, general concept and more like philosophical. And so that's, I would consider what is the overarching term. And it includes a lot of different categories below it, like machine learning as one of the major techniques is one of them. But then there are some other algorithms like evolutionary strategies, which are also considered AI since they're also following principles like human intelligence, but are actually computed very differently than machine learning. And then you could also have just very simple rule-based algorithms like for chatbots or so. And they also try to mimic human intelligence, although maybe they're very basic compared to actually machine learning or even deep learning based approaches. Mentioning deep learning, that's also a subcategory of machine learning. Everything is basically more and more complex. So it means larger networks, more parameters, and much more effort to train. But nowadays, with the computational resources, pretty much most applications are rather in deep learning, although it's still also part of machine learning. So I will mainly use the term machine learning or artificial intelligence in the next minutes. Now, basically, machine learning is already around since quite some time. So in the 50s, it was Arthur Samuel who defined it as it is to give computers the ability to learn without being explicitly programmed. So without explicit rules being already defined. Because with the classical programming approach, you define certain rules. You have some knowledge that you use, like maybe mathematical relationships or physical relationships, or just a good understanding of the problem. And then typically you also have some data, and you combine the rules with the data, then you get some answers. And for example, that's often used in GNSS processing, because you know the observation equation, you have your data, the raw measurements, and then with simple estimation algorithms like least squares, you can get your position, like the answer. With machine learning, it's a bit different. Actually, instead of having rules, you have rather the answers. So you also start with data, so you input data, but maybe from experience from the past, you already know the answer to a certain problem. And then what you do is actually you use machine learning to derive the rules. So the relationships between the data and the answers. And yeah, this concept, this can be actually maybe nicely explained with an example from the field of weather prediction. Because in the classical way of doing numerical weather prediction, where you have information about the weather condition at a certain point, like today, we know it's maybe sunny with a bit of clouds. And then you have your physical knowledge. You know all the equations that govern the atmospheric dynamics and how weather evolves. You know all the boundary conditions and all the continuity equations and so on. And then you can implement all that in a very large model, the so-called numerical weather model. And with that, you can predict the weather of tomorrow. Now, the problem is that, first of all, to describe the weather conditions, like all the atmospheric variables, it's a lot. So it takes really a lot of variables. And these numerical weather prediction models, they are really very sophisticated and require, for accurate predictions, also very high computational resources. So typically, the weather organizations, they have really large computing systems like supercomputers, clusters, to do this weather prediction. Now, on the other hand, when we go now to the machine learning concept, we will benefit from the advantage that we have knowledge about the state of the weather in the past. So we have decades of weather data where we exactly know the conditions, like at that day, it was sunny and cloudy, and on the following day, it was raining a little bit. And we can build these pairs. So again, it's like the data, so the input, and the answer, so the output. And we combine all these pairs for the history of our weather archive. And with that, we can train actually a machine learning model. And since there is a lot of data, it will actually be a very deep learning model. And we can only do that really with very big clusters, just like the weather model required before. But once we have this machine learning model, we are done with the training. We can use this prediction model, which is typically based on some neural networks or transformers, and then we can actually apply it. And operationally, we can then use the weather from today as an input. And then instead of the numerical weather model, which is really complicated, we use this machine learning-based weather prediction model, which is based on standardized algorithms, like neural networks, which are really efficient to compute. And with these, we can predict the weather tomorrow. And that we can now do actually on a small computer. Maybe you just need a GPU, a graphics card, and then it will be possible to, just for yourself, predict the weather. And actually, in the field of weather prediction, AI has played a major role. And I would say it's really now state of the art. So the AI weather models, they are outperforming traditional numerical weather models for the predictions, and they're also much more efficient. And they're also openly available. So you can actually download these models and run them for yourself. Now, this is a very broad overview, of course, only now for machine learning. Based on this example, I think you probably have now a good understanding, but let me give you a bit of a general overview for the different machine learning categories, because there are also a lot of different applications, and for these, you might need also to use different types of machine learning. So very important is also unsupervised learning. So basically, you have already your data, but you don't have any knowledge about any like structure in the data, or you don't have any labels that tell you like is the data good or bad, or is it part of a certain class or category. And so these unsupervised learning techniques, they just try to provide you with more structure in your data, a better understanding, and maybe a reorganization where you can more easily then do further investigation. So actually, one basic unsupervised learning algorithm is basically principal component analysis. It will also bring some structure in your data. It will reduce the data to certain components, the so-called principal components. And this is a very basic method, already established, of course, in the terms of statistics already, not before AI was a big thing. But then also with AI, these approaches have been becoming more and more sophisticated. Clustering, it's rather also standard, but then when we come to something like autoencoders, then it gets really to the state of the art of AI machine learning, where we, with the autoencoders, really get very good representation of data in a very efficient manner. And other very important category is supervised learning. So this is basically the approach that I've highlighted with this example from weather prediction. So it's a method that can automatically learn this relationship, these rules between the data and the answers, our inputs and outputs. And here just some examples of algorithms, like very classical ones include support vector machines, decision trees, random forests, but nowadays it's rather about neural networks, and especially deep neural networks. And yes, then there are also many other variants of that. Reinforcement learning, where you can let the models interact with the environment and then gradually improve them. Or self-supervision, which is a bit of a mixture of supervised learning, but without any clear labels. So basically in supervised machine learning, which will be the main focus of this task, is to imagine you have input data, like certain features, different variables, and then we have a target, something where we clearly want to train your model on, which you then want to determine. You also need a measure of how the model performs, like what is a good prediction. Like the weather should be correct, of course, for the next day. And you have to create a metric that measures this. Often it's like the root mean squared error or mean absolute error of your predictions. And then with that, you can estimate the parameters of your machine learning model with a technique, for example, like backpropagation, where you compute the residuals and propagate them back through your neural network, and then adapt the parameters of the network that it best fits to your observations. Different problems with supervised machine learning can be a classification, where you have discrete labels, so right or wrong, 0 and 1. Or it could be regression problems, where you have a continuous label, like typically physical variables like temperature, they are always continuous. And how you approach this problem of supervised machine learning is, first of all, you start with an architecture. You define like the number of layers, number of nodes, and you initialize this model with random weights. And with that, you compute your first predictions by using the input features, propagating them through the model, and then computing your predictions. And then you compare these predictions with your ground truth data, so your targets that you have, these labels, which allows you to compute the loss function. And then you adapt the model with this backpropagation to refine it and slowly reduce the loss. So you repeat this again and again with all your different training samples until you don't see any improvement anymore, and then you're finished with training the model. Then when you apply the model, you will use data that you have not seen. For example, you have a separate test set, which is completely independent. And then, yeah, you can apply your model and really properly assess the performance of your model. So that's the very basic strategy of applying supervised machine learning. And this can be very nicely applied to many geodetic problems. And let me give you a first example where we use it for GNSS metrology. So basically determining atmospheric parameters with GNSS. And here we really directly benefit from the fact that there are so many GNSS stations globally available. So this map here shows like almost 20,000 GNSS stations globally distributed. And yeah, we have this great data set where the Nevada Geodetic Laboratory have computed atmospheric variables like the zenith wet delay, so the corrections due to the atmospheric wet propagation delay. And yeah, that is also, of course, related to the atmospheric water vapor. So it can be used also for atmospheric monitoring. And since we have so many stations and so much data, we definitely also wanted to explore to use machine learning to better incorporate and model this data. So the goal was really to create a global model of this zenith wet delay. So this very important variable from the GNSS processing to make it available globally, and that users can use it for improving their corrections when they do operational GNSS processing. And so in terms of data, we used from almost 20,000 stations the zenith wet delay provided by the Nevada Geodetic Laboratory. So this was the target, our goal to predict this variable. And then we used a lot of different input features to support these predictions. For example, meteorological data from the model ERA 5, which is one of the best atmospheric data sets, specifically humidity, because it's very related to the zenith wet delay. And then some input related to the geometry, like the latitude, longitude, height of the stations, and also time in terms of day of year, hour of day, just to capture these many different oscillations that can appear in the data. Now here in this case, we used a machine learning algorithm called XGBoost. It's actually based on decision trees, and it uses gradient boosting to improve them. And it's a very nice algorithm since it's typically working well out of the box without too much fine-tuning. And it's also quite interpretable. Yeah, so we had our input data, all these auxiliary features, our output data, the zenith wet delay predictions, and we split the data into training and testing. And based on the training stations, we trained the algorithm, we determined all the parameters of it, we did hyperparameter tuning, so refining it, and then we were able to evaluate it on the test stations. Now, the result looks like this. So it's indeed a global model of zenith wet delay, which has been trained on the stations that we had available. And of course, we can see a very nice global coverage since we have available all our input features. So the geometric time features and also the numerical weather data. Now, that is, of course, visually very nice and meaningful, but also we wanted to evaluate it concretely. So we computed the statistics on a test set. And here we see that the performance globally is really at the level of 8 millimeters mean absolute error or 11 millimeters root mean squared error. So at the level of 1 centimeter, we can really provide global corrections for zenith wet delay. So that's practical for GNSS processing, but also it can be used for meteorological investigations or climatological investigations. Like here we have a map of the global trend that we get from the zenith wet delay. And then here we studied anomalies for different months, and you see positive and negative anomalies. And actually it's quite interesting if you compare it, for example, to climate variables or indices like the El Nino Southern Oscillation Index, then you can see quite a nice fit, which corresponds also to the zenith wet delay anomalies. Yeah, so that was one example where we use geospatial monitoring, modeling of atmospheric parameters. Now, here an example where we use AI for mass anomalies observed with the GRACE mission. So the GRACE mission uses a principle of the relative distance measurements to determine the mass variations of the Earth. So basically, when these two satellites fly over a mass anomaly, they are differently accelerated. So the satellite closer to the mass anomaly is first accelerated forward. So the distance between the satellite increases. And then when the second satellite catches up, then the distance shrinks again. And this kind of signal can then be translated to gravity field parameters that describe these mass variations. And this is really very relevant for monitoring changing masses, like related to the hydrological cycle, so terrestrial water storage, and also water in the ocean and water on the ice sheets in the form, of course, of ice then, so Greenland and Antarctica. And so since these missions like GRACE and also the follow-on mission, GRACE follow-on, can provide these variables very precisely, we wanted to explore if we can improve them further, since they are suffering still from one major issue, namely the spatial resolution. And right now that's only about 3 degrees. In terms of regional or local applications in hydrology, this is unfortunately not sufficient. So we wanted to improve this spatial resolution. For that, in machine learning and AI, there's a principle called downscaling, or sometimes also called super resolution, where actually we start with a low resolution image and then construct the high resolution data. We also wanted to apply that to the GRACE data, since we also have very low resolution, but would like to have an improved spatial resolution. Now, this is the original GRACE data as an animation, and you can see here really nicely that it is really a variable. It covers really nicely the changes in the mass, both on the continents, so in terms of water storage, and on the oceans in terms of ocean bottom pressure. But you don't see much details here because these pixels in this image, they're really very huge and they don't allow you to see any details. Now I will already show the main results of our approach, which are the global downscaled terrestrial water storage and ocean bottom pressure values that we got with machine learning. And here now it looks completely different. If you look at the continents, you can see individual river systems. Like if you look at South America, you can see nicely the Amazonas. And you see many different lakes and other structures globally. And also in the oceans, you can see really fine structures like eddies and a lot of ocean dynamics. Now, how did we get to this great result? So we applied actually a self-supervised approach here, where we not only used GRACE, but combined it with different auxiliary data sources. Since we know that GRACE can measure very accurately the mass concentration, so the values are very accurate on the larger scales. So we combined it with some data that, on the other hand, provides the higher resolution, although the data are overall a bit less accurate. And that includes, for example, hydrological models and ocean reanalysis products. So they are less accurate than grays, but they have a much higher resolution. So we wanted to combine these two data types, like the grays data and the models, to get the best of both worlds. So the accuracy from grays and the resolution from the models. And we applied this pipeline shown here, self-supervised, meaning that we have not any external labels. We just have our data, like input here that I mentioned, the grays data, the hydrological models, and some other features. And our targets are actually also a mixture of the grays and the water, the hydrology models or the ocean models. And with self-supervision, we need a more specific loss function that tells us how these should be merged together. So here we define basically how we would do this combination. And yeah, this slide also shows a few details, how our model looks like. You see a lot of different features, like we have convolutional neural networks in a residual block configuration that has worked very well for our purposes here. Now, we wanted to also make sure that we can evaluate the models properly, and that means comparing it with external sources. So for the ocean bottom pressure, we compared it to tide gauge measurements. And yeah, we have here globally like about 500 tide gauge stations where we can compute the correlation between our machine learning model, so our downscaled model based on grays, and the environmental models, and the tide gauges. And on the right-hand side, you can see the improvement in this correlation at the different stations, and you can see that most of these points are rather green, and not many points are red. So overall, we had a better agreement with the tide gauges at 80% of the stations. Now, for the terrestrial water storage, however, it's unfortunately not so easy to evaluate it, because grays is basically the only measurement technique that can really properly assess the terrestrial water storage. So here we relied on actually a principle, and that is basically the water balance equation. It tells us that the difference in the terrestrial water storage is the precipitation, so all the water that is added, minus the runoff, so what flows away, and also the evapotranspiration. And all that can be taken from certain hydrological models. And we were able to do these comparisons on a global scale. So on the left-hand side, you can see the figure where green again means that the downscaled model performs best compared to the original grays data. And it's very encouraging that pretty much everywhere globally this works very well, except for a few regions, namely in the Sahara Desert. There we have issues, but that's also because of course in the desert there is not much water to play with. And then in certain other areas, especially highly mountainous areas. But what was really revealing is that if we look at the size of these basins that we were considering here for these evaluations, we can see that with grays, it works reasonably well for maybe also the larger basins, but for the really small basins, here the downscaling approach was really helping and showing great improvements. So that is shown on the right-hand side, where all the values above 0 show that the downscaled version was better. And this is given as a function of the size of the basins. So the values on the left-hand side, they are the smallest basins. On the right-hand side, they are the largest basins. And so the largest improvements could be seen really for these basins on the left-hand side. So these really small basins, which then can only be well determined with the downscaled version based on machine learning. Yeah, now my final example is from the field of Earth orientation parameters. So we need Earth orientation parameters to do navigation, also processing of geodetic data, orbit determination. And unfortunately, the Earth orientation has a lot of variations related to external forces, like from the gravitation of the moon and the sun, but also mass changes within the Earth system, like the atmosphere and ocean. And we know these physical relationships quite well. So there's the principle of the conservation of angular momentum, which you know maybe from ice skating, where if there's an ice skater who holds out the arms very far away from the body, then the person spins very slowly. And if it's very close to the axis of rotation, the mass, then it spins very fast. And yeah, if you know these physical relationships, we also want to use it then to improve our modeling and predictions of Earth orientation. So here we focused on the so-called celestial pole offsets. So some of these Earth orientation parameters, which are especially important for navigation beyond the Earth, like within the solar system, and for spacecraft navigation. And also these are really related to the geophysical processes. So in this plot, you can see the time series of these parameters. So there are two components in X and Y direction. And here we applied a very similar approach to what I showed with the weather prediction. We have the time series of these Earth orientation parameters. We have them in the past, and we have them in the future. And on this relationship, we can train the machine learning model. Now, what we did here, which is a bit beyond the standard approach, is that we wanted to incorporate this physics, so these relationships between the variables in the Earth system, like atmosphere, ocean, and then also we wanted to properly quantify the uncertainty. And there we trained multiple models, so so-called ensemble of models. And that allows us then to assess the model spread and to determine the uncertainties. And here, just a very quick overview of some of the math that goes into that. We have some physical equations, the Liouville equations that describe this excitation, atmosphere, and ocean. And then for the uncertainty quantification, we have some other equations where you can see we have the mean, the mu, so the mean value, and then also the variance, the standard deviation, which can be computed for this deep ensemble. And all of that can be included in estimating these neural networks. So we call them geophysics-informed neural networks. And the nice thing is that we really then learn also something about our parameters. So we could really determine this frequency of a certain resonance in the time series, the so-called free-core notation. And you can see it changes over time. It's roughly 430 days. And we could also determine which are the driving forces of that. And it seems that the ocean, the oceanic angular momentum, causes about 70% of that. And the atmosphere, so the AAM, atmospheric angular momentum, about 30%. And so it's nice for physical interpretation, but also for the performance. So we did these predictions into the future of these celestial pole offsets and compared to the official products from the International Earth Rotation and Reference Systems Service, our predictions were up to 30% better. And you can see here in this plot the comparison between these IRS products, which are the full lines, which are the worst, so the highest mean absolute error for the different forecast horizons. And then our approach, so the dotted line performed better when we included this atmospheric and oceanic excitation. So the dotted line is a bit lower than the dashed line, because the dashed line doesn't include this information about the oceans and atmosphere. So that was also really good to see that including them improves also the predictions. And here you can see in this plot our predictions for these two variables. And the good thing is we have now error bars. So you can see that these curves, so the green curve in particular, has some measure of uncertainty around it. So, and that is really due to this deep ensemble approach, where we can then give the user also a level of confidence in the predictions. And overall, this is really encouraging, since with these models, we participated in this official campaign organized by the IRS, the second EOP prediction comparison campaign, and these machine learning-based models that we produced performed best in the overall comparison. Yeah, that brings me now to the end of this all these examples. So maybe just a few words on the future and what are, from my side, the main perspectives of AI and machine learning in geodesy. And I think it's pretty clear that pretty much all places in geodesy can, to some degree, benefit from different kinds of AI and machine learning algorithms, but many not all tasks. So there are definitely some problems where we can really benefit from our previous knowledge and proceed with that. And the same is true like in other fields, like in seismology or remote sensing. Some tasks have been really also advanced with the use of AI and machine learning, but also there are still, of course, a lot of classical approaches which are still very relevant. Then, it becomes, I think, more increasingly difficult to really exploit all the available geodetic data now that it's so easy to collect data, for example, with low-cost sensors, like U-blocks are very cheap, and also smartphones nowadays, they have GPS or actually multi-GNSS built in, and also CubeSats. Like here you can see for the Spire constellations, which provide GNSS radio occultation measurements, the number of data is becoming more and more. But still, I think the domain knowledge, so really the geodetic basics to interpret the data will always be essential. So basically not only having the data as an input, but also our geodetic knowledge. For example, to interpret disturbances in the time series, could it be an earthquake? Could it be actually an antenna change? Who knows? Challenges, of course. We need to select the proper data, do pre-processing. As I mentioned, data quality is really essential, and then properly train the machine learning models. So I think for that, it's really important to increase also the education about AI in school and universities, since it's becoming more and more important. And then, another issue, of course, this trust and interpretability is often a bit neglected in machine learning, since they're quite complicated, so often referred to as black boxes. So I think here, something with explainable learning, with uncertainty quantification, feature importance are really important. And then, physics-informed learning can also really help to get a better understanding what the algorithms are doing. With that, I want to wrap up this talk. I think AI and machine learning shows great promise in geodesy. I have showed some examples for atmosphere, gravity field, Earth orientation parameters, but there are many more potential applications. The same for the different problems or tasks, like machine learning is great for spatiotemporal modeling, downscaling, forecasting, but what I've not shown, for example, anomaly detection. And finally, I want to just highlight again, we hopefully try to improve the transparency of the results with approaches like physics-informed learning and uncertainty quantification. With that, I want to thank you very much again for this great opportunity to present here, and I'm really looking forward to discussing and hearing your questions. Thank you.
Thank you a lot, Professor Benedict Soya. We have some questions in person right here at UNESP from Professor Tainá. She have a question for you. So Tainá, feel free to make your question.
Hi, Benedict. Good afternoon. Congratulations for your presentation. I am researching postdoc and I work with neutral atmosphere and the modeling. And I would like to know, do you use SMWF and VMF products to calculate the ZWD or another model?
Yeah, it's a very good question. And ECMWF, these are really the best atmospheric data that are available, I would say. So there's this reanalysis dataset, ERA5, which is really the state of the art of atmospheric datasets. And it's actually the foundation of many geodetic products based on the atmosphere. And in terms of determining the zenith wet delays, these are actually based on the Vienna mapping functions also, so the VMF one was used for that. And actually, I have to say that there's also the potential to use machine learning to determine mapping functions. And this is another ongoing study that we are looking into. So in principle, it's very flexible and can be applied in many different problems, including atmospheric monitoring and also mapping functions and GNSS processing.
Okay, thank you. Thank you for it.
Thank you.
Okay, for our last question, we have another question from YouTube chat that Professor Elmo Tanahura left for us this comment. He told, how would you classify in terms of AI, machine learning, and deep learning, an automated tidal prediction app with parameter inputs, LLM-based chat, and a cartographic station selection interface?
Oh, that sounds like a really exciting application, I have to say. So I would say it has different components here, right? So the LLM-based chat is certainly, I would say, AI. So these are really based on really large models, typically billions of parameters estimated. And so that's typically referred to as AI models. Now, the part about the tidal prediction, I don't know, maybe it also uses some kind of machine learning algorithm. Then I guess it depends a bit on what was used there. Some simple neural network, then it could be machine learning, or if it's something sophisticated, then maybe deep learning. But yeah, overall, if you just combine everything, I would say it's really something AI-based, yeah.
Okay, unfortunately, we don't have any time to answer the last question from YouTube chat, but if you want, you can answer Professor Galera. He wrote an important question in the YouTube chat. So we will need to move on to the next presentation. So I would like to congratulate you and thank you again for your excellent presentation.
Thank you again for the opportunity. It's really great to be here.
Thank you, Professor Benedict. At regard. So moving on for the next presentation, I will say for you em português. Então, para a próxima apresentação, gostaria de chamar o professor Roberto Teixeira Luz, do IBGE. Antes disso, gostaria também de pedir para que vocês pudessem confirmar suas presenças com o QR Code que estará aparecendo aqui na sua tela, ok? É apenas apontar o seu celular para o QR Code e anotar a sua presença. Professor Roberto, fique à vontade e tenha uma excelente apresentação. E muito obrigado pela cooperação.
Obrigado, pessoal. Obrigado pelo convite. Boa tarde a todos e todas. Muito bom falar para a comunidade de vocês, da nossa comunidade, na verdade, e ainda mais com uma data tão bacana como esses 80 anos em que a gente, aqui no IBGE, comemora o início dos trabalhos de nivelamento geométrico. Então, não coloquei meu nome aqui justamente porque é uma marca conjunta aqui, colaborativa, da comunidade ibegiana de Geodésia. E a gente tem muita coisa para falar, então vamos direto ao assunto. Antes, porém, tem uma figurinha bem básica aqui que mostra o estado de integração atual de todas as sub-áreas da geodésia, nivelamento, gravimetria, GNSS, tudo junto no que vai ser o brevemente lançado IHRF, um dado global de altitudes. Vamos lá. Então, antes de começar, só para sempre deixar claro que todo o material, ou quase todo o material que a gente vai discutir aqui, está no site, no portal do IBGE, na internet, e nesse portal um pouco separado, que é artigos.ibge.gov.br. Vamos lá. Dado vertical, tradicionalmente em geodésia a gente usa o nível médio do mar, né? Tem umas outras aplicações que usam outros níveis de referência, como por exemplo o nível de redução para cartografia náutica, A gente vai mudar isso, daqui a pouco vamos comentar um pouquinho melhor sobre IHRF. Eu gosto de chamar as estações de IHRF de marégrafos secos, porque vão dar uma referência para a rede independente dos fenômenos oceanográficos e meteorológicos. Me desculpe. Então, eu já comentei isso. A integração desses dois níveis de referência, ou desses dois conjuntos de níveis de referência, seria objeto de uma outra palestra completamente independente e bastante longa também, o tal do problema alt-bat, em que a gente precisa integrar nível de redução da cartografia náutica com o datum vertical da cartografia terrestre para aprimorar o modelo geoidal, ou os modelos geoidais, justamente na região onde ele é mais necessário, que é a zona costeira, mas é um outro assunto. Então, a partir do datum vertical, definido tradicionalmente numa estação maregráfica, nós transportamos as altitudes, por meio de desníveis que foram observados com nivelamento geométrico e também com gravidade. Antigamente nós não tínhamos, no início do levantamento geodésico, não tínhamos cobertura gravimétrica adequada, então se utilizavam modelos teóricos da gravidade. A gente vai ver isso mais tarde também. Mas eu gosto de incluir essa figurinha aqui, que a gente vai ver daqui a pouco com mais detalhes. E, finalmente, uma outra introdução que eu gostaria de dar é justamente o fato de que a superfície de referência ela é materializada a partir das altitudes, ou seja, de cima para baixo. Isso é importante porque cada vez que a gente muda os dados de entrada, os dados considerados no ajustamento, a gente muda o resultado, ou seja, a gente muda a superfície de referência das altitudes. Isso dá origem àquilo que a gente chama de realizações da componente vertical do sistema geodésico brasileiro, sempre tendo aquilo em vista, A gente define o sistema geodésico de referência, nesse caso, o sistema geodésico de referência vertical, e depois a gente materializa, a gente realiza esse sistema por meio de uma rede e outros conceitos associados e outros elementos associados, como as coordenadas, por exemplo, no caso são as altitudes. Então vamos lá, evolução da materialização. Todos nós conhecemos os marcos geodésicos, mas antigamente eles eram um pouquinho diferentes. Coloco isso aqui justamente para mostrar que existe uma adaptação ao longo do tempo. Por quê? Porque quando o IBGE começou a fazer gravimetria de forma sistemática na década de 90, não era possível colocar o gravímetro nessas RNs, cujo topo era um quadrado muito pequeno. Então, foi necessário mudar o modelo de marco. Posteriormente, muito mais recentemente também, a gente adaptou, nem todos os marcos, mas alguns marcos a gente adapta trocando a chapa, aquela chapa cravada no topo do marco, por um dispositivo de centragem forçada, favorecendo a ocupação GNSS nessas estações verticais, de modo que não haja aquele erro absurdo na medição da altura da antena com tripé ou com bastão. Na verdade, a gente até evita bastão, falando de aplicações de alta precisão, porque ele é meio instável, e tudo mais. Mais recentemente ainda, nós adaptamos e adotamos aquele conceito de marcos profundos, ancorados aqui no substrato mais estável, de modo que as variações verticais do solo, as camadas superficiais, não afetassem a posição vertical. E adaptamos também um conceito que os franceses introduziram de triplets. Então, essas estações de hastes profundas podem ser agrupadas em grupos de 3, de modo que a eventual destruição de uma ou até 2 não compromete a estrutura de suporte de uma rede de precisão científica como essa que eu vou mostrar agora, rede geodésica de referência costeira. Justamente foi um experimento que o IBGE fez aqui no litoral do Rio para lidar com aquele problema alto-bate, a integração das superfícies de referência no litoral, na zona costeira. Então, alguns triplets foram colocados, foram instalados, e todo o nivelamento aqui, mais de quase 1.400 quilômetros, 81% desse nivelamento está com 1 milímetro raiz de quilômetro. Então, um nivelamento muito bom, mas a gente tem que tomar cuidado. Como é que se faz isso? Coloquei essa figura aqui, uma só figura para falar dos diversos erros sistemáticos ou efeitos sistemáticos que afetam o nivelamento geométrico de alta precisão, mostrando que o nivelamento geométrico é uma operação bastante simples, né? Mas a física por trás dele é extremamente complexa. Então, por exemplo, o aquecimento aqui da atmosfera, ele sempre acontece de baixo para cima. A insolação aquece o solo, e o solo é que aquece as camadas da atmosfera. Então, nós precisamos sempre olhar para onde nós vamos apontar o nosso nível, onde é que vamos colocar as nossas miras, pensando no pavimento, evitar asfalto sempre, evitar diferenças de meio ambiente, aqui de visada, de qualidade de visada entre ré e vante. Não basta manter a distância igual entre ré e vante, tem que ter a mesma qualidade. Se é sobre grama ré, a vante também tem que ser sobre grama, para que não haja diferença de percurso óptico. Nesse caso aqui, por exemplo, a refração residual ela vai ser mais exagerada, porque não vai se compensar simplesmente com a distância. Então, isso também seria uma palestra diferente aqui, com mais assuntos detalhados. Então, vamos em frente. Tratando agora da gravidade. Sempre aqui sob a supervisão do nosso querido Gauss, né? Foi ele que introduziu essa ideia de que o nível do mar, ele nem falava em nível médio, né? Ele só falava nível dos oceanos, seria um parametrizador para uma superfície de referência. Depois é que o Listing introduziu o nome de geóide. Mas, voltando aqui, qual é o conceito? Um oceano idealizado, homogêneo, em repouso, também uma litosfera e um corpo planetário homogêneo. Nessas condições, a gravidade ela é bem comportada e ela define uma superfície que a gente chama de equipotencial, mas para todos os efeitos é uma superfície horizontal também. A definição de superfície horizontal ou equipotencial é exatamente essa, superfície que é ortogonal em todos os seus pontos ao vetor gravidade. Então, ótimo, essa situação é beleza, mas é uma situação altamente idealizada. Introduzindo só uma pequena complicação aqui. Um monte submarino é um ajuntamento de massa, uma anomalia de massa. Essa anomalia de massa, pela lei da gravitação universal de Newton, provoca uma distorção do campo de gravidade. Os vetores de gravidade são desviados em direção a esse ajuntamento de massa, e as superfícies horizontais se ajustam a essa deflexão dos vetores de gravidade. Então, de forma contraintuitiva, eu gosto muito dessa figura porque é contraintuitivo. As superfícies horizontais se afastam das anomalias positivas de massa. Se fosse aqui uma fossa oceânica, seria o contrário. É uma anomalia negativa de massa, os os vetores eles se afastam dessa anomalia negativa de massa e a superfície horizontal tende a apontar para dentro da anomalia negativa de massa. Isso considerando oceanos. Para ressaltar esse conceito, eu coloco aqui as bolhas dos nossos equipamentos topográficos e geodésicos, mostrando que mesmo com essa deflexão, com essa inclinação da superfície geométrica, inclinação geométrica, a física da coisa não é alterada, continua sendo uma superfície horizontal, a bolha continua calada. Então é interessante sempre reforçar esse conceito, porque não é tão natural assim. A gente olha para isso aqui e acha que vai rolar a água ladeira abaixo. Mas isso aqui não é uma ladeira, para a água não é uma ladeira. E aí, indo na direção dos continentes, a bagunça, a heterogeneidade na distribuição de massas é maior ainda, né? Daí vem a necessidade de a gente ter gravidade sempre em conjunto com o nivelamento geométrico de alta precisão. E aí a gente substitui o desnível puramente observado no nivelamento geométrico, a gente substitui por uma diferença de geopotencial, ΔC. É importante fazer isso, é importante agregar o valor médio da gravidade numa seção qualquer ao desnível observado no nivelamento geométrico. Eu não gosto de chamar o desnível de desnível geométrico, porque desnível geométrico tem uma definição rigorosa em geodésia. É o desnível que a gente obtém quando faz a diferença de duas altitudes geométricas. Altitudes geométricas são aquelas que não levam em conta o campo da gravidade, são altitudes elipsoidais. E aqui o nivelamento geométrico leva em conta o campo da gravidade, então é uma outra coisa. Talvez uma definição melhor seja desnível nivelado, alguma coisa desse tipo. Só para diferenciar, o número esferopotencial é justamente obtido na falta de observações da gravidade, como no passado. Antes de 2018, o IBGE adotava esse conceito aplicando a chamada correção ortométrica, que na verdade era uma correção normal ortométrica, usando o gama, que é a gravidade teórica, gravidade normal, obtida com fórmulas bem tranquilas de se calcular, de se avaliar, e aí se tentava corrigir o efeito das variações do campo da gravidade. Só que esse modelo ele é simétrico em termos do elipsoide de revolução, simétrico em relação à rotação do elipsoide, né? Simétrico em longitude. Então, por exemplo, para linhas de nivelamento que sobem a Serra Geral, Serra do Mar, de Imbituba para o interior do estado de Santa Catarina, na direção leste-oeste, a gravidade teórica não serve para nada, não corrige porque não tem variação de latitude nesse caso. Então, o ideal é sempre contar com observações da gravidade em todos os pontos do nivelamento. E o conceito do IHRF está aqui, que a gente vai falar um pouquinho e depois complementa. O W0, que é o potencial, o geopotencial do geóide, foi obtido por observações de altimetria por satélite, vai servir de superfície, ou vai servir de definição da superfície conceitual de referência. O IHRF, o pessoal, os grupos de trabalho definiram a metodologia para calcular o geopotencial nas estações de referência, estações GNSS contínuas, que além de terem X, Y, Z, vão passar a ter também o W. E aí, com essa diferença aqui, a gente obtém um ΔW, que dividido por um valor de H qualquer, ou de H não, desculpe, de G, né, vai dar o valor de altitude de referência. Aqui, só para constar tipos de altitude, ressaltei os tipos que a gente já teve no Brasil. altitude normal ortométrica, que pega o número esfero-potencial e divide pela gravidade média na vertical, a gravidade teórica. E a altitude normal, que é adotada hoje, pega o número geopotencial, com valores observados da gravidade, e divide pelo mesmo valor médio da gravidade teórica na vertical. A altitude ortométrica rigorosa não é facilmente obtível, porque tem um valor médio na vertical da gravidade observada. Mas como é que a gente obtém o valor médio na vertical entre a superfície e o geóide? É difícil a gravidade observada, né? Então é complicado. Essa tabela aqui só para mostrar que a altitude normal não é uma invenção do IBGE. Na verdade, a maioria dos países adota a altitude normal, porque ela dá uma padronização bastante benéfica para o sistema geodésico global como um todo, mas tem alguns outros casos, né, alguns outros países que adotam outros tipos de altitude. Mostrando agora a evolução do sistema vertical, começou lá com alguns nivelamentos do Serviço Geográfico do Exército, então Serviço Geográfico do Exército, SGE, na década de 1910, alguma coisa em 1920 também, mas grande parte foi nas décadas de 40 e 50, mais ou menos quando o IBGE começou a fazer o seu nivelamento também. Então, em azul aqui a rede do IBGE partindo de Torres, né, com referência a Torres, e em vermelho a rede observada pelo SGE, pelo então SGE, e em amarelo o que era planejado que eu não consegui confirmar se chegou a ser observado ou não. Então, em 1945, em outubro de 1945, 80 anos atrás, o IBGE iniciou seus trabalhos lá no sul de Santa Catarina e rapidamente progrediu em direção ao norte para cobrir o território como um todo. Essa sequência aqui vai ser bem rápida, só para ressaltar alguns fatos importantes. Eu vou colocando aqui os ajustamentos, que a gente chama de ajustamentos históricos. Os dois primeiros são objetos de publicações. Os dois primeiros são referidos a torres. Então, vamos lá. Em 48 foi o primeiro, em 52 foi o segundo, fez o reajustamento do que já tinha sido feito. O terceiro ajustamento em 1959, aqui, exatamente. Esse foi o primeiro ajustamento referido a Imbituba e foi o último dessa série de ajustamentos históricos que foi global. Os demais foram feitos parcialmente. Por exemplo, esse quarto ajustamento, 1962, fixou as altitudes aqui de ponto de contato com os ajustamentos anteriores e só ajustou esse bloquinho. Da mesma forma, os demais. Esse esquema aqui de evolução de 2 em 2 anos também é legal para mostrar que quem for trabalhar com altitudes e por algum motivo acaba tendo que lidar com altitudes em banco de dados, em registros históricos, que não tem muita documentação, é importante ter uma ideia dessa progressão e dessa sequência de ajustamentos, que às vezes a gente pega empreendimentos, obras, grandes obras de engenharia em que não está claro da onde veio aquela altitude que eles usaram de referência. Talvez essas informações aqui possam ajudar. Então, tem documentações lá no portal do IBGE que podem facilitar esse trabalho. O trabalho de interpretar as relações entre os diversas altitudes. Continuando, então, até o último ajustamento, em 1975, último ajustamento histórico, né, feito manualmente, sem ajuda de computadores. E vejam que foi uma progressão mais ou menos ao longo do litoral, né, com algumas centenas de quilômetros aqui em alguns pontos, mas sem uma grande interiorização. Mas a rede já estava sendo interiorizada. Esses ajustamentos aqui não foram objeto de ajustamentos dessa série de ajustamentos históricos. Depois foram foram objeto do primeiro ajustamento computacional que o IBGE fez na década de 90. Continuando aqui, após os ajustamentos históricos, a medição continuou, né, com a interiorização, e aí na década de 80 o IBGE voltou à região sul, porque o Exército já não fazia a implantação da rede de nivelamento, não trabalhava mais com geodésia sistemática, né? Então, muita coisa para cobrir destruições, o índice de destruição é alto, e no Nordeste houve um projeto específico que era altitudes das sedes municipais. Todas as sedes municipais tiveram linha de nivelamento, geralmente linhas abertas, né, ramais, para levar altitudes a essas sedes municipais, ao 100, altitudes das sedes municipais. E até que chega a situação atual, cada mês com algumas dificuldades de orçamento e pessoal, e o nivelamento vai diminuindo. O IBGE ainda faz nivelamento, mas não no ritmo que já tinha alcançado lá na década de 70, com mais de 1.000 quilômetros de nivelamento por ano. Comparando, então, o primeiro ajustamento computacional na década de 90 foi feito com a blocagem naquilo que a gente chamou de macrocircuitos. Foram ajustados esses macrocircuitos, depois os circuitos internos, a propagação dos desvios padrão nas altitudes ajustadas é essa que está sendo mostrada aqui, 13 centímetros, um pouquinho mais de 13 centímetros aqui no extremo da rede, no extremo norte da rede, né? E a diferença em relação aos ajustamentos históricos. Essa também é uma informação importante para quem for trabalhar com altitudes antigas, mostrando justamente aquela história de que onde tem ajustamento, onde aconteceram os ajustamentos históricos, as diferenças em relação ao primeiro ajustamento, aos ajustamentos computacionais, né, as diferenças são bem comportadas. Já no interior, não, as diferenças são mais significativas. Já em 2011, foi a primeira vez que se aplicou a técnica de Helmert Blocking com um pacote computacional canadense, que permitiu a gente eliminar algumas distorções daquele esquema de blocagem com macrocircuitos. E, finalmente, em 2018, a gente aplicou a mesma técnica de Helmert Blocking com a integração de valores de gravidade observada pela primeira vez. Isso nos permitiu fazer a conversão das altitudes que eram normais ortométricas em altitudes normais rigorosas, levando em conta o campo da gravidade. Isso foi um grande ganho para o sistema geodésico brasileiro. Então, no caso, a comparação dessas altitudes normais e das outras altitudes com os níveis médios em alguns marégrafos mostra algumas características locais e uma característica global que é justamente o aumento, o comportamento, a variação positiva do nível médio do mar à medida que a gente segue em direção ao Equador. Por quê? O nível médio do mar nas águas quentes ele está mais alto, porque é uma água mais quente, a coluna de água ela sobe um pouco. Nas latitudes mais próximas dos polos, a água mais fria, a coluna de água tem uma altura menor. Isso também não acontece só no Brasil, tem um exemplo muito bacana na Austrália, só que não dá tempo da gente mostrar isso, né? Isso é o que era chamado topografia do nível médio do mar ou topografia dinâmica dos oceanos. Mostrei nos marégrafos a comparação das altitudes. Uma outra comparação em outros pontos, mostrando que as diferenças elas variam de acordo com a região da rede. Por exemplo, aqui ao longo do reservatório de Itaipu, lá na fronteira oeste do Paraná. As diferenças das altitudes de 2018 em relação às demais as anteriores históricas, né, 81, e as demais, de 92 e 93, que é o AGP, e o ajustamento em 2011, mostram que essas últimas duas, as diferenças das atitudes atuais, normais, em relação a 92 e 2011, são mais ou menos iguais, por volta de entre 10 e 15 centímetros. Só que aquela altitude lá de 81 tem uma diferença mais significativa, justamente já fazendo uma referência àquela outra figura que mostra que os ajustamentos históricos não chegaram lá no interior, tá? Tendo uma diferença um pouco maior. Uma outra figura parecida, mostrando que o comportamento é completamente diferente, é aqui na cidade do Rio. Uma distância bem menor também, 45 quilômetros, um pouquinho mais de 45 quilômetros, que mostra que os diferentes pares de altitudes têm comportamentos bem específicos. Tá? Mostrando para vocês a importância de entenderem como são as altitudes da rede do SGB na região de trabalho de vocês. E, finalmente, depois do Real de 2018, nós precisamos atualizar um modelo para conversão. Por quê? Justamente fazendo referência àquelas primeiras observações lá no início da palestra. A superfície de referência é uma específica para cada realização, para cada ajustamento. E não é o geoide, não é o modelo geoidal, porque as altitudes não são ortométricas, rigorosamente falando. Então, e também não é o quase geoide, porque a gente optou por manter os data verticais, de Mituba e Santana. Então, a gente chama de datum vertical brasileiro. E por que a gente tem que atualizar? Porque, como todos sabemos, as altitudes que vêm do GNSS são altitudes geométricas, elipsoidais, e não são compatíveis com a maioria das aplicações de engenharia. A gente precisa de uma conversão. E quando a gente usa modelos geoidais, o resíduo é muito alto. Tem uma lacuna aqui naquela equação. A gente precisa de um modelo que se aproxime mais do datum vertical. Como é que a gente faz isso? Justamente modelando esses resíduos observados nas estações onde se conhecem os dois tipos de altitudes. As estações que a gente chama de SAT-RN, conexões entre nivelamento e GNSS. E aí, fazendo isso, a gente obtém, a primeira vez que a gente fez isso foi com a HGOH 2020, né? E isso é importante salientar que é um modelo, então ele não reproduz todos os detalhes da variação do datum vertical. É uma modelagem suave, então existem resíduos em todas as estações. E esses resíduos são uma indicação da qualidade do modelo na região de trabalho. É um outro aspecto que a gente precisa levar em conta quando estivermos planejando nossos trabalhos. Em cada região, o modelo vai ter uma certa característica. Então, você pode verificar como está o modelo HGOH 2020 na sua região de trabalho antes de se despencar até lá. Eu vou mostrar já essa verificação, mas antes disso, antes de ir lá, é importante sempre ressaltar aquela diferença. É sempre melhor tentar fazer uma aplicação relativa do modelo. Se tem uma RN do IBGE na região de trabalho, preferencialmente mais que uma, você pode ocupar essas RNs com seu GNSS para verificar como está o modelo, e essas diferenças que você encontrar, você aplica aos pontos em que você precisa da altitude. Isso vai te permitir, por exemplo, vencer essa diferença sistemática nessa região específica aqui. Às vezes isso não é possível, então só nos resta aplicar o modelo no modo absoluto. Esse é o modelo. Na verdade, essas aqui são as correções em relação ao modelo base. Qual foi o modelo base para o HGO-HNOR 2020? É o MapGeo 2015. Então, as correções na região de Imbituba, as correções variam daqui do máximo de 45 centímetros na região da Serra Catarinense, até um mínimo de 90 centímetros negativo aqui na região de Roraima, Amazonas e Roraima, né? E na região de Santana, ao contrário, justamente pelo uso do dátum de Santana, que é fortemente influenciado pela água doce do Amazonas, né, pela aquela imensa descarga fluvial, os sinais se invertem. As correções ao MapGeo do HGO-HNOR 2020 são da ordem de 60 até 85 centímetros. Aqui nesse outro cartograma são os desvios padrão dos fatores de correção, tá? Variando de 4 a 13,5 centímetros. Outra coisa para se ressaltar é essa região do extremo oeste do país, no Acre e Amazonas, em que a gente não tinha estações SAT-RN próximas o suficiente para a gente considerar viável, tecnicamente, prolongar o modelo. Então, o IBGE tomou a decisão de manter o MapGeo 2015 aqui. Só que a gente conseguiu melhorar um pouquinho a cobertura aqui no Acre, algumas estações SAT-RN no ano passado, e no próximo ano nós vamos lançar uma nova versão do HGO-HNOR que vai acabar com essa ausência de modelo integral aqui cobrindo o extremo oeste do país. Isso é uma certa dificuldade, isso introduz uma certa dificuldade em algumas aplicações e a gente quer evitar essas dificuldades. Tá? O resultado é o modelo, né, o modelo base mais as correções gera o HGO-HNOR 2020. Sempre lembrando aqui, a quem já usou o serviço de cálculo disponível lá no portal do IBGE sabe que quando cai nessa região aqui, o modelo indica MapGeo 2015, porque não é possível calcular as correções sem a contribuição das RNs, das altitudes da rede altimétrica. Só para ter uma ideia, no caso da região de Imbituba, foram 1.270 quase estações utilizadas, dessas 35 foram rejeitadas com o critério de 3 sigma. Antes da rejeição, o RMS era de 10 centímetros, depois da rejeição, 6,5 centímetros. Tá? E esse indicador aqui é só um indicador daqueles 5%, né, acima de 1,96 sigma, os 2,5% para cada lado da curva normal. E aí nós fizemos alguns testes internos usando outros modelos. Tá? Por exemplo, o GEOID 2021 e QGEOID 2021, calculados pelos nossos colegas lá da USP e da UFU, professor Gabriel, professor Denizar, professora Ana. Os dois modelos de 2021 eles foram divulgados no ISG, International Service for Geoid. Eles foram divulgados em 2022, se eu não me engano, e aí nós fizemos um cálculo para ver como se comportava. E, de uma forma interessante, um outro aspecto que é contraintuitivo, o modelo resultante tem uma aderência muito melhor aos pontos SAT-RN. Isso significa que o desvio padrão geral, ou RMS geral, é mais baixo. Sendo mais baixo, o limite as tolerâncias para rejeição 3 sigma também são mais apertadas, e aí gera uma rejeição maior, níveis de rejeição bem maiores. Tá? Mas os indicadores de qualidade são mais ou menos compatíveis. Tá? E aí, mais recentemente, os mesmos colegas liberaram os modelos de 2023, né? Geoide e QGeoide, e a gente fez um cálculo rápido só com o QGeoide 2023 para ver como eram as coisas. Houve um pouquinho mais de rejeição no caso do QGeoide, mas os indicadores de qualidade são bem parecidos. Provavelmente a gente vai usar um desses modelos do quase geoide para calcular a próxima versão do HGOH9. E aí sim, aquela tabela que eu tinha mencionado, é importante, essa tabela está no site, lá no portal do IBGE, portal do HGOH9, disponível para os usuários verificarem como está o HGOH9 2020 na região de trabalho de cada usuário. Então, analisando os resíduos, você pode saber se está tranquilo, se os resíduos estão mais variados, ou se é necessário procurar RNs do IBGE para melhorar o modelo. Então, é importante dar uma olhada nessa tabela, né? E aí, exemplo. Um outro exemplo, no caso da usina hidrelétrica de Itaipu, do reservatório, né? Aqui em azul são os resíduos negativos, bem próximos do reservatório. Em vermelho, resíduos positivos, um pouco mais afastados. A amostra não é tão boa assim, mas parece indicar um certo efeito sistemático, né? Entre pontos mais afastados e mais próximos do reservatório. Seria interessante investigar melhor isso. Essa figurinha aqui ao lado é só um refinamento dessa primeira figura, com uma casa decimal a mais, e com os resíduos daqueles dois modelos, o QGeoide 2021 e o QGeoide 2023, mostrando que em alguns casos os resíduos melhoram e em outros casos eles pioram, né? Por exemplo, aqui era 7.9, passou para 8.1 e para 10.4, sempre HGOH 2020 oficial, depois o cálculo com o QGeoide 2021 e o QGeoide 2023. Então não tem fórmula, cada caso é um caso, em cada estação a relação entre eles vai ser diferente. É importante verificar sempre como está a sua região de trabalho. E lógico, quem tem um GNSS geodésico e vai a campo pode contribuir, tanto para a avaliação do modelo atual, como para o refinamento do próximo modelo. Para a avaliação do modelo e para o refinamento, como é que você submete os seus dados? PPP, né? Todo mundo conhece, ou quase todo mundo conhece e usa o PPP do IBGE. Para colaborar, basta informar. Se ocupou uma RN, informa o código da RN aqui nessa caixa. Lá na página do PPP é só informar o código. Se puder contribuir mais ainda, adota as especificações do IBGE. Lá nas especificações de 2017, que estão disponíveis na página do IBGE, a gente coloca, para ocupação GPS em RN, 3 sessões de 3 horas cada uma, beleza, você consegue fazer uma contribuição muito boa para esse caso de cálculo de modelos para conversão de altitudes. Sempre insistindo, entre as sessões você mexe no tripé, altera a altura da antena, que você você permite uma obtenção mais robusta da altitude geométrica daquele ponto, daquela estação. Fechando então com o IHRF. O IHRF vem sendo discutido e testado e calculado e refinado, a metodologia de cálculo, né, nos últimos anos. No caso do Brasil, as últimas avaliações dizem que está muito bom. O grupo que calculou aqui no Brasil a solução chegou num indicador de qualidade muito interessante. Existem algumas soluções melhores aqui em outras áreas do mundo, mas a nossa está melhor do que a maioria delas. esse e outros slides próximos foram retirados dessa apresentação aqui da Laura Sanches. E aí, nossos colegas que eu já mencionei, Gabriel, Denizar, a Ana Cristina, eles avaliaram, comparando os resultados os valores do IHRF para a América do Sul, com aqueles dois modelos que eu já mencionei, que eles calcularam. E aí obtiveram para o Brasil uma avaliação muito boa. O problema maior está na região montanhosa, né, nos Andes. Mas aqui no Brasil as diferenças são bem consistentes. Então a gente está muito bem na foto. Coloquei essa informação aqui só para vocês entenderem. O IHRF ainda não foi divulgado. Ele já está calculado, mas ainda não foi divulgado. Por quê? Porque não basta jogar um número na praça. Tem que ter uma estrutura organizacional que dê suporte a isso, a manutenção do sistema e ao aprimoramento, né? Então, essa e as próximas versões serão baseadas no trabalho daquilo que eles estão chamando de Centro de Coordenação do IHRF. O endereço é esse aqui, tem muito material lá para vocês consultarem, é interessante todos se colocarem a par. No Brasil, 6 estações, foi a configuração que era possível de trabalhar naquele momento, né, porque precisava de muita gravimetria, algumas estações não, mas principalmente Marabá, por exemplo, que foi a estação mais adequada que a gente conseguiu definir aqui na região norte. Mesmo assim demorou muito, a gente ainda está fechando alguns detalhes, né, a coordenação de geodésia do IBGE está fechando alguns detalhes. Só para ter uma ideia, esses círculos concêntricos aqui são um padrão que o pessoal do IHRF definiu como orientação para as autoridades geodésicas nacionais. E aí, no caso da estação Marabá, o IBGE resolveu adotar a especificação deles de distribuição de pontos para os compartimentos mais externos. Vejam aqui que as estações gravimétricas são mais espalhadas. Nos compartimentos mais internos, de 100 km para dentro, a gente densificou com 5 minutos, que é a densidade de pontos adotada em todos os demais trabalhos gravimétricos do IBGE para cálculo de modelos geoidais. Além disso, a gente resolveu aproveitar a existência de uma segunda estação RBMC relativamente próxima de Marabá, que é Imperatriz. Por isso que isso aqui tem o círculo aqui, estava deformado, né? Não é deformado não, é porque tem 2 círculos aqui, Marabá e Imperatriz. Então nós fizemos 2 estações, nós fizemos observações gravimétricas e de nivelamento em 2 estações para chegarem para definir 2 estações IHRF. Por quê? Porque Marabá precisou de tanto nivelamento que o nivelamento, com um pouquinho mais de esforço, chegou à Imperatriz. Isso permite que o resultado do IHRF, que a coordenada vertical do IHRF, seja avaliada de forma independente se a gente usar os resultados do nivelamento com gravimetria. Então é exatamente isso que a gente pretende fazer e, de repente, até tentar aplicar isso para as próximas versões do IHRF, aplicar isso em outras regiões, para confirmar de forma independente a metodologia do IHRF, comparando a solução do problema de valor de contorno com o nivelamento mais gravimetria. Se está tudo certo, se tem alguma coisa para se refinar. Quem acompanhou as discussões do IHRF viu que não foi fácil, eles tiveram que fazer um experimento chamado experimento Colorado para aparar as arestas entre as diferentes metodologias para a solução do problema de valor de contorno da geodésia, e isso permitiu um enorme desenvolvimento teórico e metodológico na geodésia física. Então, era isso. Eu acho que talvez eu já tenha passado um pouco aí, vocês me desculpem. Tem muita coisa para falar, mas em termos de rede vertical, de componente vertical do sistema geodésico brasileiro, mostrei um pouco do passado, como estão as coisas atualmente e para onde a gente acha que vai caminhar. E fico agora à disposição, agradeço aí novamente o convite do Gege, a assistência de todo mundo aqui numa sexta-feira à tarde. Valeu, pessoal.
Perfeito, muito obrigado, professor Roberto, pela excelente apresentação. Gostaríamos agora de irmos em direção, iniciar, né, a nossa sessão de dúvidas e comentários. Já temos 2 no chat do YouTube, na verdade temos até 3. Então vamos ter essas 3 e aí nós já vamos para a finalização da nossa reunião. Então, começando com a dúvida do professor Felipe Nevinski. Boa tarde. Para melhorar a densidade das medições gravimétricas, seria mais vantajoso fazer gravimetria terrestre ou aerogravimetria?
Do ponto de vista técnico, de resolução espacial, a gravimetria terrestre, sem dúvida, seria a melhor opção. Nem sempre isso é possível, né, Felipe? Porque a gente tem regiões que não dá para fazer, não dá para densificar muito. Cobertura florestal, áreas protegidas, como parques nacionais, terras indígenas, territórios tradicionais, né? Então, áreas montanhosas. Então, às vezes, isso é difícil. Existe essa alternativa da gravimetria embarcada em aeronaves, mas ela ainda é muito cara para os padrões brasileiros, né? E a gente não tem essa cultura de aplicar a aerogravimetria para a geodésia. Tem algumas iniciativas de aerogravimetria para exploração geofísica, né? Principalmente para exploração mineral, mas ainda a gente carece de uma movimentação para tornar isso mais uma aplicação mais comum. A gente vê que eu outro dia conjecturei que a gente poderia pensar em outras plataformas, por exemplo, por que não dirigíveis? Mas aí é uma conjectura muito louca, né? É uma discussão aberta.
Perfeito, professor. Para a segunda questão aqui, nós temos aqui a questão do professor Lucas Calado, da UFPE. Roberto, vale a pena fazer uma nova definição das coordenadas altimétricas com a série temporal de Imbituba com maior duração?
É interessante, obrigado, Lucas, por esse comentário. É interessante porque o IHRF vai trazer uma mudança de visão, né? Antes a gente precisava dos marégrafos, das estações maregráficas, para definir uma origem. E aí, por sorte, no Brasil, historicamente, a gente usou apenas uma origem para a rede, para grande parte da rede, né? Então, a gente usou Imbituba e propagou essa origem para o restante da rede, e a pequena rede do Amapá, que desconectada do resto, usou o dado de Santana. Poderia ter sido pior. Os australianos, na década de 70, usaram 30 estações maregráficas num ajustamento que definiu o datum vertical deles. E agora não, né, mas já há alguns anos, eles já vinham detectando distorções na rede vertical, justamente pela topografia do nível do mar, porque eles têm a situação geográfica bem parecida com a nossa. Tem águas frias no sul, águas equatoriais no norte. E aí a topografia do nível médio distorceu completamente a rede vertical deles. Quando compara com altitudes de GPS, de GNSS, algumas fontes dizem até 1,5 metro de tilt, né, de inclinação. Então, o problema de usar observações oceanográficas, né, maregráficas, para definição de datum vertical, de redes geodésicas, é esse. A gente não tem muita possibilidade de controle. Ou você usa uma só, ou usa várias, tenta corrigir a chamada topografia dinâmica, mas é meio complicado. O IHRF eliminou isso e, na verdade, melhorou a condição para os oceanógrafos, porque agora as altitudes da rede altimétrica referidas ao IHRF, elas são completamente independentes daquilo que se passa no meio marinho. Então, a rede altimétrica agora passa a ser, de fato, uma referência para a observação do nível do mar e para controlar o movimento. Então, se você tem uma estação RBMC numa estação maregráfica e chega a rede altimétrica junto, referido ao IHRF, você vai ter o controle geométrico das possíveis variações crustais ali com a RBMC, e você vai ter o controle físico com as altitudes IHRF, dando a referência para o que está acontecendo no nível médio do mar. Passa a ser um controle independente, de fato. A rede geodésica auxiliando no monitoramento do nível do mar, sem precisar desse monitoramento. É uma outra história. Por isso que eu gosto de chamar de marégrafos secos, porque a gente fica independente dos marégrafos para a definição do dato vertical. Na verdade, a gente continua precisando integrar estações maregráficas na rede vertical para dar suporte aos usuários que precisam das relações entre os diversos níveis de referência. Por exemplo, o outbat. O problema outbat não vai ser solucionado sem que a gente tenha muitas estações maregráficas integradas na rede vertical, na rede de nivelamento do SGB.
Bom, professor Roberto, temos ainda mais 3 questões no chat, mas eu vou apenas selecionar uma do professor Leonardo, para não excedermos muito no tempo. Porém, para aquelas questões faltantes, eu vou enviar por e-mail com cópia aos que estão perguntando as mensagens e as dúvidas para o senhor, ok, professor?
Sim.
Ok, então para a última dúvida do dia, o professor Leonardo Castro Oliveira, do IME, mandou: Oi, RL. É válido dizer que o usuário pode encontrar uma diferença maior do que os resíduos encontrados pelo IBGE, pelo fato dos valores dos usuários não pertencerem à amostra do cálculo?
Resíduos encontrados pelo IBGE aonde? Eu não sei se eu entendi a pergunta. Seria interessante esclarecer isso. Resíduos do HG ou HNOR, por exemplo, ou são resíduos no ajustamento de 2018? São 2 tipos de resíduos diferentes. Né?
Pensou eu que a altitude encontrada pelo HG ou HNOR em relação a talvez de um dado, por exemplo, obtido em uma RN e um dado obtido arbitrariamente?
Sim, faz sentido isso que você falou. Pode encontrar uma diferença maior que os resíduos? Pode, o usuário pode encontrar resíduos maiores ou resíduos menores também. O fato é que a gente não tem muito tempo, né? Então eu não deixei de falar muitas coisas. Um aspecto relevante desses modelos para conversão reside no fato de que são quatro observações ou pressuposições no cálculo de um modelo para conversão. Você precisa da fonte de altitudes físicas, da fonte de altitudes geométricas, precisa do modelo base, e aí com esses 3 elementos você calcula o resíduo. Considerando, aí a quarta condição considerando que a estação seja a mesma entre nivelamento e GNSS. Geralmente, a diferença de tempo é bem grande entre o nivelamento e o GNSS. Geralmente, o nivelamento é muito mais antigo, do que o levantamento de GNSS. E aí você reza para que aquela RN esteja no mesmo lugar. Às vezes não está. Às vezes não está por motivos de um afundamento, né, de um recalque natural do solo, ou até mesmo um soerguimento natural, alguma raiz de árvore que pode estar elevando a RN lentamente. Mas às vezes a gente sabe, né, o padre, o secretário de obras, o pessoal que não conhece, acha que vai preservar a RN, retira ela, ou vai fazer uma reforma numa praça, retira para fazer a reforma e coloca de volta no lugar. Eu tive o maior cuidado para colocar no mesmo lugar, está lá direitinho. Não está, né? Então, é uma dificuldade. A gente tem muitos assuntos de estudo no cálculo desse tipo de modelo para conversão. Por exemplo, seria interessante introduzir uma ponderação no sistema de equações, na solução da colocação por mínimos quadrados. Seria interessante colocar uma ponderação proporcional ao tempo decorrido entre um e outro levantamento. Talvez, porque dá para conceber que quanto maior o tempo decorrido, maior a chance de uma movimentação da RN. É uma conjectura, tem várias outras, né? Então, tem muita tese, muita investigação científica aí, ou acadêmica para os nossos companheiros e companheiras professores que possam avançar nesses assuntos.
Perfeito, professor Roberto. Gostaria de parabenizá-lo novamente e também de agradecer por todas as contribuições e também por essa excelente apresentação, professor. Alguma consideração final a fazer?
Não, só agradecer mesmo o convite, e é uma demanda muito urgente para a nossa comunidade de geodésia ter mais oportunidades da gente se reunir online assim, apresentar as nossas atividades. Nós precisamos disso, dessa interação entre a comunidade acadêmica, a comunidade produtora e a comunidade usuária de dados e informações geodésicas. Então, vocês estão de parabéns aí por manterem essa sequência de seminários e que siga por muito tempo aí. Parabéns.
Perfeito, professor. Que venha 2026. Muito obrigado, professor Roberto. Eu gostaria também de agradecer a todos que aqui estão presentes, a todos que estão presentes virtualmente pelo canal do YouTube, e gostaria também de chamar o professor Galera para dar uma palavra final em relação ao nosso seminário anual do Gege. Professor Galera, você já está online, fique à vontade.
Já estou online, né? Deixa eu tirar aqui a cozinha aqui. Bom, pessoal, mais um Gege anual, que eu diria, do meu ponto de vista aqui, foi bastante produtivo, muitas coisas novas, assuntos interessantes, alguns deles que a gente já tinha algum conhecimento, outros novos, e eu espero que todos tenham aproveitado. Quero deixar o meu muito obrigado aos participantes, quer seja presencial ou virtual, aos palestrantes, e aí você, João Zalpa, e o Lucas, que trabalharam aí para organizar essa apresentação virtual e online, e todos os demais que estiveram envolvidos na divulgação, Tainá, Carol, Dani, e sigamos em frente. Próximo ano estaremos aí. Quero desejar boas festas para todos, Natal, Ano Novo, e que em 2026 voltemos com todas as forças e muito trabalho e resultados positivos sejam realizados. Muito obrigado a todos.